to tutorial class today. In this short video, I'm going to be introducing us to what we call computer aided drug design, or normally called CADD, and molecular modeling. Several persons before now have been confused in one way or the other on what CADD actually means. What is it, and then of what relevance is it to different scientific researches, and what are the different tools involved in this, who and who should be involved in CADD and who shouldn't be involved, what kind of researches necessitates the use of CADD tools and what others do not. So hopefully in the course of this video we are going to be addressing some of these. All right, as a way of outline, we are going to be looking at the following outlines. The first one is what is actually CADD, while secondly we'll be looking at what is molecular docking as a tool in CADD, all right, and then we also consider the different steps, involved in performing molecular docking, including the post-docking analysis. Also, we will be looking at ADMET analysis of prediction and drug likeness property estimation. And finally, we'll consider molecular modeling and lead compound optimization, as the case may be. All right, when we talk about CADD, we're simply talking about findings or developing and analyzing medicines or bioactive compounds from plant extracts or from synthesized products, all right, using computer aided methodologies. All right. For so many of us involved in different areas of research, ranging from drug discovery, from plant extracts, or synthetic chemists that are continually involved in the synthesis of varying bioactive compounds or potential drugs. All right, CADD encompasses the tools or the use of tools, or methodologies to investigating the therapeutic, properties of these plants or these synthesized products. All right, many of us before now may have heard of, some kind of researches such as anti-diabetic effects of some plant extract, be it root, be it leaf, or anti-inflammatory effect of this plant bark or this plant root and all that, which is not far from, what forefathers carry out in folklore medicines, all right, where a particular root or herb, all right, is being made into concoction such that when a member of the family, all right, is not feeling too well, a cup of this is always given to the person, and in most cases, after a while, such person begins to recover. All right, so it's believed that in that particular concoction, which is actually an extract, all right, because most of them mixes either the bark, the root, or the leaf in an extractant, all right, which could be ethanol, methanol, aqueous, which is water, as the case may be. So at the end, there is a kind of maceration kind of extraction, all right, where the component of those plant extras, upon incubation in this extractant leaks, all right, into the extractant, which could be water, like we mentioned, ethanol or methanol, as the case may be. So at the end, upon consuming the liquid portion of this particular mixture now, these compounds at the end try to exhibit some therapeutic, properties and all that. So it's similar thing that CADD helps you to investigate, but in this case, in a more technologically developed or advanced manner, where a particular plant of interest, which could be a plant bark, plant leaf, or the root, is meant to pass through extraction, all right, The obtained fractionated, all right? The obtained extract is made to pass through fractionation, using different extractant. In this case, you try to maximize the different components of this particular extract, all right, by passing through a fractionation column where different extractants will be, passed through the same extract, all right, enabling the extraction of different components of that particular extract, dissolving at different polarity of the different, extractant. So at the end, the obtained fractions, all right, is further characterized using tools such as HPLC, GCMS, GCFID to simply identify the individual active ingredients or active compounds, all right, present in this particular extract. Upon discovering these active compounds, one will certainly find out why they exhibit the acclaimed therapeutic properties, all right, or effects they do when used in medicines or even in folklore medicine and all that. All right, so we will also consider the use of CADD methodology, as a way of speeding up, the stages or the early stages of chemical or drug development, in a way of guiding and speeding up drug discovery. All right, it's also a reasonable and methodical technique that concentrates scientists' attention, all right, on the most promising chemicals or drug candidates, eliminating a whole lot of unneeded, efforts in trying to carry out such task in the laboratory, leading to a whole lot of trials and error and all that. So the use of CAD actually help to eliminate such kind of occurrences. All right. By way of continuing, we also try to consider what has CAD actually come to do when compared to the conventional way of drug development, which we actually used before the emergence of CAD tools and all that. Yeah, over the years, in the past years, we discovered that drug development involved a whole lot of processes. All right, it involved a whole lot of processes that as well consume a whole lot of years, efforts, money, and all that. All right, from what we can notice here, we discovered that before a particular compound is optimized for uh, drug or is finally developed into drug and sent to the market, you spend over 10 to 12 years doing that, and this most time costs over $1 billion and all that. All right. However, the emergence of CAD, you discover will certainly or has certainly um reduced that, all right, where you can now have up to just about 3 to 5 years to develop a particular drug. So it actually came to enhance the conventional way of drug development. All right, in CAD we have two basic approaches to computer aided drug design. All right, for those that would actually want to venture into this properly, you discover that in CAD we have two basic approaches, like I mentioned. The first is structural based drug design, which is always called SBDD, and the ligand based drug designing, which is the LBDD. Okay, in structural base, we simply investigate the drug potency or the drug candidacy or the therapeutic effects of a particular synthesized product or a lead compound or active ingredients with respect to a known 3D protein or a known 3D structure of a particular receptor. All right, you get a particular receptor, a particular protein, which is generally called a target. All right, you have your target and you now investigate the interaction of different compounds or different active ingredients or synthesized products of yours against this particular protein. However, this particular protein or receptor or target in quote should of course have great uh, you know therapeutic implication. All right, it must be involved in the metabolism, of what you are investigating, the effect you're investigating. For instance, if you're investigating anti-inflammatory effects, it should be the protein or the receptor involved in the catalysis of the rate determining step, all right, of this particular uh, mechanism. For instance, in anti-inflammation, you discover is the production of prostaglandins, all right, from arachidonic acid that actually leads to the expression of inflammation and all that. So when prostaglandins are overproduced, you discover that there are cases of inflammation to occur. So what do? You tend to inhibit the point or the committed step of this prostaglandin production, all right, which is the conversion of arachidonic acid to deoxidized prostaglandin G2. All right, so if you inhibit this particular step, you discover that it will be shut down. So in structural based drug designing, we get this particular target, which could be protein or receptor or even RNA, as the case may be, and simply do what? Try to, interact that with our different compounds or synthetic or synthesized products. However, in ligand-based drug design, we only have what we call our target. All right, we have our target, which could be our receptor, our protein, or RNA, and using that to investigate, ligands, all right, that could actually bind to, all right, the protein, okay, we have, or the target we have. So in structural base, you have your protein or you have your target, and then you have your ligand, using the ligand to interact with the protein. However, in ligand base, you only have your ligand without a protein. So you use the ligand to sort the protein. So you are eventually using your ligand to investigate the proteins your ligand could actually interact with properly and all that. So that's the two major approaches which applies, all right, in CAD and all that. Okay, also we have few advantages of CAD, which we have indirectly mentioned earlier. One of it is cost effective, it saves time, is rapid, and is an automated process. All right, yeah, it certainly does that. It's also can be used to obtain idea about drug receptor interaction pattern, yeah, which is a whole lot of guide in drug development. Also, it minimizes the synthetic and biological testing efforts, okay, which usually results in loss of trials and error. So what do? You use CAD investigation to, limit some of these, and at the end you have a better output. Also, it minimizes chance of failure, all right, in the final phase, which is actually true. Okay, in the outline, we mentioned molecular docking as a tool in CAD. Yeah, many people have been wondering what is molecular docking, what is molecular docking, all right, who should get involved in this, and where can this be applied and all that. So we consider molecular docking as a tool, all right, or a key tool in structural molecular biology and in computer-aided drug design, all right, which is actually true, okay, because this particular tool aims to carry out a ligand protein docking, okay, which entirely what predicts the predominant binding mode, okay, or pose of a particular ligand within a protein, okay, certainly of known structure or of elucidated structure. All right, so docking will help you to bring a target and a ligand or a synthetic product or an active ingredient together, trying to investigate their predominant binding modes, all right, and then their strength of interaction as well. The strength of interaction of these active ingredients or these synthesized products in comparison to maybe standard drugs or co-crystallized ligands, as we are going to see later. You discover that this could give you an insight of what, the structural binding relationship of these particular ligands and the target could look like, even eventually when developed into drug and all that. All right, and these actually involve few or a whole lot of processes. However, we will come to know about that later. All right. Okay. Before we move to the next, if you look at the right side, you will see a lead compound. This is a compound here. All right. Yeah, trying to interact. This is a pocket of a particular ligand, and these are the amino acids. All right. The active site amino acid interacting with this particular. As you can see, the positioning of the ligand within the active site of this particular protein. So the predominant binding pose or mode, the nature of interaction and the strength of interaction as well gives you an idea of what this is all about. All right, we also have types of molecular docking. Yeah, there are actually a few types of that. The first one is protein ligand docking, all right, where a particular target, as you can see, is docked against a particular ligand. All right, you have the complex. This is the protein, and then this is the ligand in the active site. All right, while we also have what we call protein docking. Yeah, where two proteins are meant to dock or are commanded to dock together for a particular purpose. All right, maybe you are investigating the effect of a particular complex in a particular catalysis or mechanism of reaction. So you could actually join or dock a protein against each other, as you can see here. Yeah, in few cases, we also have the third one we call RNA ligand docking, or even RNA protein docking. All right, where a particular ligand or lead compound or active ingredients or even a peptide, a protein, yeah, could be made to dock against a particular RNA of interest, depending on the um, designed investigation or study. All right, in molecular docking, we make use of few tools, all right, depending on the nature of study you're carrying out and the choice of the computational biologist. Yeah, the first tool we have here is the Autodock Vina, yeah, which most people actually make use of because it's more affordable, all right, and is also very much acceptable in different kinds of study. So there are also free academic versions of it as well for uh, individuals interested in this. All right. So you have Autodock Vina. Okay. You also have the second one, which is Schrodinger Mistral. All right, which is an extension of Schrodinger suite. Yeah, it also has an academic version where you can make use of as a student or a researcher. All right. Thirdly, we have the molecular operating environment (MOE). Yeah, this is actually one of the sophisticated tools we use here, and might not be found or seen in the academic version of it. All right, but if you can access the full suite, is very important too. Also, we have the Pyrex. The Pyrex is another tool that in most cases is used for, kind of cloud docking, all right, or what they call multiple docking at a time. Pyrex helps you to carry out this kind of virtual screening where lots of ligands are docked against a singular target. And also, we do make use of online servers for uh, docking purposes. Example of an online server is a Patchdog, all right, where you can actually perform docking online. All right, we also have a few steps in molecular docking, which I'm quickly going to, tell us here, as this video is meant to be an introductory video. Yeah, at the end of this, I'm going to be introducing us to a particular series of classes or tutorial. Okay, for those interested in this, it will actually help you, gain some ground and proper understanding of what these different steps are all about and how they are performed one after the other. Okay, the first thing we have in steps in molecular docking is the pre-docking activities. Yeah, these are the activities you carry out prior to docking process. The first is identification of a target, all right, and ligand or compound for docking. Yeah, I've mentioned earlier you need to take time to identify your target of interest before you commence your docking process. All right, you don't just dock against any kind of target or any protein or receptor. Yeah, your target of interest must play a crucial role, all right, in the mechanism of the disorder or the disease you are investigating. Yeah, it must, most times is actually the protein, okay, involved in the catalysis of the committed step, or what we call the rate determining step of that particular reaction mechanism, of which when you shut down, when you inhibit, the rest of the pathway is caused to, to shut down or to cease. So it's these targets that we actually want identify when investigating any particular uh, effect. We have mentioned earlier something like anti-inflammatory studies usually you um, targets or proteins such as cyclooxygenase 2, all right, because of the role it plays in converting arachidonic acid to um, prostaglandin G2, which is the oxidized form of that will be further reduced in the second site, leading to inflammation and all that. So you identify the target. Secondly, you carry out what we call active site study of the target. Yeah, you need to investigate the active site of this target to avoid binding or targeting a particular wrong pocket in your protein. All right. Most times by default, your for those involved in this already, by default, you might target, due to the tool you're using, the tool might actually target a wrong pocket or a predominant pocket in that particular protein, especially proteins that have more than one binding site. All right, you might not really be able to know the actual site or the main site for drug targeting, all right, if you didn't carry out some level of investigation before that. And to do this, existing literatures can actually enable you to do this. An instance is in cyclooxygenase 2. If you have investigated such target before, you discover it actually has two major binding sites. We have the membrane binding site and the peroxidase binding site. The membrane binding site is the committed step or the committed site of the production of prostaglandin. All right, that's the first step where arachidonic acid is converted to prostaglandin G2. All right, and further reduced at the second site, the peroxidase binding site that has a heme group. So because of the presence of the heme group, the pocket is quite wider and larger than that of the first binding pocket, which is the membrane binding pocket, which is actually a drug target or targeting site and all that. So if you simply carry out a blind kind of study here, you certainly go and you start interacting your or investigating your compound or synthesized product with respect to the peroxidase binding site, ignoring or forgetting the fact that the membrane binding domain is actually where you're supposed to investigate. So trying to carry out active site study will help you curb some of these errors. And in most cases, you might not find out until you are almost done with the whole thing, for those that will even find out eventually. All right, thirdly, you also source the targets and ligands. Yeah, we have repositories, we have, um, you know, uh, sites, websites, all right, or servers where you could actually source for this. Yeah, for your targets, you might have the protein data bank. For your ligand, you might have the PubChem and all that. And then how you go about them, uh, we will introduce you to that later on. All right, after sourcing that, of course, you prepare the ligands and the targets, okay, prior to docking. And then lastly, you prepare a particular file we call the configuration file. Yeah, that will help you, perform the docking process eventually. How to do this, you will find that in our subsequent videos, which we are going to introduce you to afterwards. All right, we also have the docking activity. This is where you carry out the structural or the structural activity relationship analysis of your compounds, okay, or your identified compounds or your synthesized product and all that. Okay, this is where you actually perform the docking process proper, where you must have carried out all these pre-docking activities. The next is now to perform the docking process, by commanding the necessary tools and all that to perform the docking. And then after the docking, you proceed to your post-docking analysis, where you can now visualize the product of the docking. All right, how was the docking done? How were the poses or the predominant positions, or how was their strengths and all that. All right, usually you would visualize this in the 2Ds and the 3D structure for proper understanding of what happened. And then lastly, you carry out also what we call the ADMET predictions, all right, or what we call the drug likeness property estimation or prediction. Yeah, this is where you find out how the nature of the compound with respect to the properties of a drug. All right, does it meet some of them, or does it disobey some of them? Could it actually be proposed for drug development, or does it need further optimization for a better product? All right. Um, yeah, quickly, let's look at application of docking. Yeah, few persons might ask why docking, do we actually need docking, what studies or what kind of study involves docking or requires docking and all that. Yeah, virtually a whole lot of areas of scientific researches are currently involving this, all right? Uh, and here we'll try to highlight few of them, while many more you can investigate afterwards. All right. The first is enzyme mechanism studies. All right. You could use the tool or the docking process to investigate enzyme substrate interaction and catalytic mechanisms. Yeah, how a particular uh, target interact with a particular substrate or ligand. Okay, while performing a particular catalysis and all that could be investigated using molecular docking uh, tools. All right, you can also design enzyme inhibitors or modulators for therapeutic purposes, which is what CADD is also all about. Yeah, through molecular docking, you could design inhibitors of a particular enzyme or target or receptor, all right, for therapeutic purposes. Also, for structural based design, we also find out that molecular docking could help you in rational design of ligands or drugs or drug candidates, as the case may be, based on the three-dimensional structure of a particular target. All right, docking will help you to establish that. Also, it will also enable you to optimize lead compounds for improved binding affinity, all right, and specificity. After docking process, you should be able to, say a little about the compound, about the synthesized product, and how and where such compound or product could be optimized for a proper or a better binding affinity and specificity. All right. Also, other forms of applications here, you might find the prediction of binding affinity, all right, in vitro screening as well, in fragment-based drug design, okay, in homology modeling and structure prediction, you also have that. And it also goes beyond this, including those in toxicity study, all right, bioremediation study, and all that. Docking process encompasses all that, all right, where a particular toxicant is being investigated against a particular, target. All right, you are trying to see how this particular toxicant in the environment affects the health of the occupants of this particular environment. Yeah, you simply use this tool as well to carry out such investigation. All right, as part of our outline, we also mentioned about molecular modeling and lead compound optimization. Yeah, when you finally carries out your docking process, and then you discover that your compound or your synthesized product is actually promising. However, maybe it's not competing favorably yet with already existing drugs, already existing inhibitors. What do? You might have to go further for molecular modeling or lead compound optimization, where your compound or synthesized product is intentionally, built or intentionally, uh, raised in terms of the quality, all right, you intentionally increase the quality of this particular compound or product, all right, trying to increase the binding affinity. When I mention quality, I mean the binding affinity or specificity, or rate of interaction of this compound with respect to the pocket, which is actually a product of what? The binding affinity of that particular ligand against that pocket. So example is what we did here. So you discovered that lead optimization is the final phase of drug discovery. And this focuses on optimizing different characteristics of your lead compound, certainly, such as the target selectivity, the biological activity, the potency, and of course the toxicity potential as well. So these are what you, as a computational biologist, you carry out after your docking process, when you must have ascertained that this product or this compound could do this and this. You might go ahead to make it better and all that. Example is what we have here, all right, and there are also few tools that can help you do that, like what you have here. I actually used molecular operating environment for this particular purpose because of how it is built, unlike most other tools. Yeah, here we don't um, blindly alter the structures of our compound, or blindly add for some functional groups to our compound, in a way of trying to optimize that. No, we simply try to locate our compound or product within the active site of our target and try to see the points of limited interactions, and where these how these interactions could be built, or optimized for a better product. As you can see, in doing that, we had to, turn on our vector. As you can see, these kind of pointings are what are our vectors, which try to show us points of possible interaction, including those that are yet to be to be exploited. As you can see, we can see some whitish patches and some cyan patches. The whitish patches here will always signify the hydrogen bonding, while the cyan are examples of or indications of lone pairs within your active site. So these are one of our major points of target while optimizing your compound. So as you can see here, where my cursor is, you discover there is a particular cyan patch here, all right, which I could cause my ligand to actually do what? Interact with, all right, as a way of optimizing this compound. And this is what I have here. So I've been able to, install what we call a pharmacophore, which is just a sign at this particular point telling my compound why maintaining the normal structure of the compound. I'll tell the same compound to do what? Kindly make sure you interact at this particular point, or you extend to this particular point, in a way of trying to uh, get a better product of my compound. So this is what we have here. And then in the next slide, you discover that, yeah, this is the normal compound. Why this is my model? You discover that the rest of the compound, the rest of the structure of this particular compound is the same as in this. However, this extended portion of this compound was made to make an interaction at this cyan patch. Just like you can see a cyan patch interaction here, you can see one here, and all that, you can see one here, which is exactly what is happening here. Whereas this is still limiting, so I had to uh, quickly exploit this particular point of interaction and see how this could get better. All right, okay, let's see what happened after this particular optimization. Yeah, so when we look at this, actually, all right, anti-malaria drug I worked on in the past. All right, so you discover that upon optimization, the binding affinity of the model was certainly improved. All right, the model has, uh, began to bind with about negative uh, energy of 12.1. All right, while the normal compound or the original compound is giving us negative 10.9. However, when you compare this to existing anti-malaria drugs such as artemisinin, which has minus 8.9, you have lumefantrine, which has minus 9.4. Artemether this, even when a combinatorial therapy was performed, I had to combine artemether and lumefantrine here as well, and at the end we still find out it's having about 11.9, which is still lesser than the optimized product and all that. So this is what led compound optimization of molecular modeling could, result to. All right, as you can see, when this is located in 3D form within the active site, you can see this is the optimized product, while this is the original compound. You can see the original compound and its limited interaction. You can see the optimized compound making more interaction, causing or forming a beta inhibitor of this particular protein when compared to the other. This is actually a plasmepsin protein for those that have worked on this. All right, quickly we look at the pharmacokinetics and ADMET prediction. Yeah, most people do wonder or do ask what does this actually means. Yeah, after investigating the therapeutic properties of your compound, it don't just end by ascertaining the binding pose or affinity of your compound with respect to a target. You also need to carry out or investigate the pharmacokinetics and ADMET properties of it. All right, the drug likeness properties of it. Like we have earlier mentioned, ADMET means the absorption, the distribution, the metabolism, excretion, and toxicity property of a particular compound. Each drug candidate will always have these properties. So you need to investigate that and be able to say, oh wow, this has good binding affinity, they have good binding pose, and they also have good drug likeness properties and all that. As you can see by a table at my right, this is an example of a study I did not long ago, all right, where a particular compound, I titled compound A, all right, from a particular product or particular plant is investigated um, against a standard drug, ibuprofen. All right, so you can see the phytochemical properties, you can see the drug likeness properties, and you can see the pharmacokinetics properties. So this is an excerpt or an example of the table that helps you to um, summarize the nature or the drug likeness property of your compound or your synthesized product, all right, which needed to be attached to your work as well after performing docking and all that. Of course, when you go through that, you see the different properties of this particular compound. Okay, lastly, I might also wish to introduce us to what we call molecular simulation. People might wonder, are they actually the same thing? All right, molecular docking and molecular simulation. However, they both are important tools of CADD or computer-aided drug design or discovery. All right. However, in molecular docking, you are simply investigating your compound or your product, synthesized product, against a rigid body, all right, against an elucidated 3D structure, rigid 3D structure of your protein. However, in molecular simulation, you do this in an environment that is flexible, all right, in a moving environment, trying to replicate, the nature or the environment of the system. So normally, after molecular docking, when your compound is promising enough, you are supposed to pass that through a simulation as well to further establish few things concerning the same compound and interaction for a more informed drug development. So we discovered that molecular dynamic simulation predicts how every compound in a protein or other molecular system will move over time, all right, based on the general model of the physics governing interatomic interaction, of course. It's also one of the most prominent drug discovery tool in science and engineering, widely adopted in the application ranging from drug discovery to material design. Of course, the fidelity of the predictions of molecular simulations hinges on the reliability and accuracy of the chosen force fields as well. So when you get into this, you discover about force fields and how these, all right, play a great role in these kinds of investigation. An example is what you are seeing by my right. All right. Indirectly, I've mentioned the difference between these two. Yeah, they are actually different. All right. They're actually different. In molecular docking, you don't carry out the interaction in a moving environment, all right, or against moving atoms and all that. While in simulation, you do that. So docking is like a preliminary step to investigating your drug, like drug nature or drug candidacy of your product or synthesized compound. So what do you do after your molecular docking when you have identified your lead compound, all right, or have optimized it? You could go ahead to simulate that to find out about the final product, which will certainly inform your choice um, afterwards. All right, by way of conclusion, molecular docking and simulation have greatly, impacted several fields of scientific research. Okay, so and as such, should be optimized or optimally maximized, all right, globally for an improved research outcome. Certainly, CADD and molecular docking tools or computational biology tools has, room to find several roles to play in different kinds of researches, ranging from macromolecule investigation, structural investigation, interaction and all that. There are a whole lot you can actually do using these tools, all right, which the more you come to make use of them, the more you actually find out where more can actually be applied. All right, this.
Okay, you are welcome to this section of the training or tutorial on molecular docking. In this particular video, I'll be showing us how we can assess our working materials, which includes our protein or enzymes or receptors, as the case may be, and also our ligands or substrate we want to work with or want to dock with. Okay, so I've opened my browser. As you can see, this is Chrome. You can use any browser of your choice. And before you go to source your material, you must have settled down to read about what you want to do, what protein do you want to work with, what are the ligands or substrate you want to dock them with, okay? You're supposed to have read around these proteins or ligands, okay? And when you read about them, you will possibly find out their data bank ID number, okay? Every protein has an ID number through which you can search, for it, okay, and you get it. Or if you don't have the ID number, you must have had your protein in mind, okay? So what you do, you will log on to the website I'm about to enter and then search for your protein, okay? Quickly, you go to your browser, you search for PDB, okay? PDB simply means protein data bank, okay? This is PDB homepage, okay? Once you open it in your browser, okay, you're going to click on the first option here, which is this, okay? When you click it, it will log you onto the next page in your protein data bank, okay? Look at what I have. This is PDB by RCSB, okay? This is protein data bank. This is where you can access any protein or receptor you want to work with, okay? Simply by the right top side, as you can see from my cursor, you will see this is an option where we can search, okay? You either search for the name of the protein here, or you search for the ID number, okay, of the protein, and you will find it, okay? I have already made my research and I have found I'm working with acetylcholine esterase, okay? Acetylcholine esterase, okay? and the ID number I'll be working with is 2ACE. Okay, you can search for yours and get your own ID number, but mine I've got this because I've read about the protein. Okay, so I'll simply type 2ACE, be it small letter or be it capital letter, it will open it. Okay, I'll click on search. Once I search, it's supposed to bring me to the protein I just looked for now. Okay, the page is loading. Yes, it has loaded. Okay, it has loaded. So this is what I have. This is my protein. Okay, and this is the protein I searched for. This is what 2ACE, which is a native acetylcholinesterase from Torpedo californica. Okay, this is what I have. So what do I do after this? These are different informations you can find about your protein. Okay, how many chains do you have there? This is the molecule, these are the chains, these are the sequence lengths, this is the organism that produced it. Okay, these are more details, okay, you can find about your protein. You can read around this more on your own. Okay, so what do I do after I locate my protein? I'll simply go to download files. Okay, I'll click on download files, and you will see different formats of this particular protein I can download. Do I need the faster sequence? Of course I don't, for what I want to use it for. Okay, so what I need is the PDB format of my protein. Most protein, while downloading them, download them in your what? In PDB formats. Okay, some of our docking tools only recognizes protein in their PDB format, or if you happen to download in other formats, you must have to convert them to PDB format before you could make use of them. So this is PDB format. So I will click on PDB format. Okay, and it will start my download. Okay, you can see by my down left side is already downloading my protein. Okay, this is my protein downloading here, and it has already been downloaded. Okay, if I click on this arrow, it will ask me to locate the folder where it has gone to. So I will click on show in my folder. Okay, if it has downloaded, I'll see it in my folder. This is under my downloads. Okay, you can see my protein is already downloaded, and you can see the icon there, which is BS. This is Discovery Studio. That's the file, the document or the app, the software. Okay, the default software I have in my own system. So your own system may have a different default software. Okay, but it's just the format that matters, which is our PDB format. Okay, so I've already downloaded my protein, so I can continue, go to my download and do what, and access my protein and continue to work with it. Okay, thank you and see you in our next video. Okay, hello, welcome to this video. In this video, I'm going to be showing us how we can read around a bit our protein or receptor of interest. Okay, so many people have complained of not being able to know the particular protein to download from PDB page. Okay, sometimes you search for a particular protein and you see so many results. So many are complaining or are confused on which particular one to make use of. Okay, so it's always preferable if you're into such issue, or you happens to even run into problem of not knowing the particular protein to even search, okay, in your PDB database. You're searching and you're getting a different result. Okay, what you simply do is come to your browser and search for the protein outside the PDB platform. For instance, I want to search about acetylcholine esterase, so I'll simply search acetylcholine esterase. Okay, this is what I have. Okay, I'll click on it and it will load. Okay, this is acetylcholine esterase that's loaded. Okay, so you can see different informations about acetylcholine esterase you can read about. Okay, these are different things about you can read about, but here I'm simply looking for acetylcholinesterase, okay, so I can be able to know which PDB format of it I want to make use of. Okay, to do that, you can simply look for it in their Wikipedia form. Okay, this is their Wikipedia site. This is acetylcholinesterase. I'll simply click on the Wikipedia. Okay, Wikipedia will expose a whole lot of information about your protein of interest. Okay, a lot of information. Look at the acetylcholinesterase. This is the Wikipedia query or answer of it. Okay, you will see a lot of information about your protein. Okay, or your receptor of interest and the rest. Okay, even your ligands, you can Google them on your page and check before if you have any issue or question about it. Okay, as you can see, as I scroll down, I've got to my available structure. This is telling me that acetylcholinesterase actually have a structure, and this is the structure on Wikipedia. Okay, so how do I now get the PDB ID I can use to download this particular structure from my PDB? You can download the structure from here. Okay, as you can see under the structure, it will refer you to the PDB, okay, or the RSB. Okay, it is the same thing. Okay, you can either click any of these, or you can simply tap on the image. When you click on the image, it will load this way. Okay, once it loads, scroll down a bit. Under the image, you will see acetylcholinesterase. This is the PDB rendering based on 1B41 structure. Okay, this is the 1B41 structure. This is one of the structure Wikipedia pick out of the many structures you can find in your PDB bank or your PDB data bank. Okay, so what do? I've known that this is 1B41, so I can go to my PDB data bank and search for this particular ID number. So I'll simply copy it or write it down somewhere. Okay, I can copy it or write it down somewhere. I'll now go to my PDB page. Okay, I'll simply search for my PDB and it will load. Okay, once PDB loads, I'll go to my home page. Okay, this is the home page. It has loaded. Okay, so I'm supposed to search for that particular protein now. Okay, I've already copied the ID number, so I'll simply click on this and paste it. Okay, this is 1B41. Okay, so I can easily search for it. It's supposed to take me to acetylcholinesterase. Okay, a structure I can make use of for my what? My molecular docking studies. Okay, as you can see, this is human acetylcholinesterase. Okay, this is human. Okay, this human acetylcholinesterase complex with this and that. Okay, so this is the acetylcholinesterase. So I can easily download it from here through the PDB format, and it will be downloaded to my to my system, and I can now prepare it and use it for my my molecular docking studies. So this is another way you can search for your protein. Okay, in case you're confused on the particular protein to make use of, or you are not seeing the particular protein you're actually looking for. You simply go to your Google and search the protein. If you still can't find the information, go through the Wikipedia page of the protein. It will expose you to a few other information about the particular protein. And then you can, from there, pick even the ID number and then come to your PDB page and download it and make use of it for your molecular docking studies. Thank you so much. Okay, you're welcome back to this tutorial. Okay, in this section of the video, I'll be revealing to us how you can access your ligands or substrates you want to dock with your choice protein or receptor. Okay, so quickly I've launched my browser. This is Chrome. You can use any browser, Opera Mini, Firefox, or any of them. Okay, so how do I access my ligands? Ligands are stored or are found in a database called PubChem. Okay, PubChem is a database that houses lots of ligands or chemicals or substrates as the case may be. Okay, so I'll quickly go to my search and search for PubChem. Okay, this is my PubChem. Once I search for my PubChem, it will load, and this is the home page of PubChem. Okay, upon the home page being open, you simply go to this first section here and click on it. This is PubChem what homepage. Okay, this is where it will take you to. Okay, once it has taken you to this place, the next thing is to type in your ligand of interest or your chemical of interest or substrate of interest. Here, because I'm working with acetylcholinesterase, I've picked a pygenin, okay, as my substrate. Okay, if you got your spelling very well, under it you will see different forms of your substrate or your ligand. Okay, meaning I got my spelling very well, so I'll simply click on search. Okay, and once it's search, it's trying to locate my ligand. Okay, as you can see, it has loaded, and this is my ligand. If you scroll down, you see different forms of your ligand, either where is in complex with something else or different forms of it or isoforms of it. Okay, so the first option is usually made use of if it's just the default or native of the ligand you want to make use of. These are different other names, okay, of this particular ligand. So I'll simply click on the ligand, okay, and it will load. Okay, it's loading my ligand. Okay, it's trying to open it. Make sure you are connected to a strong network, okay, to be able to access some of all this. This is a database, and as such, a lot of information is being stored here. Okay, my ligand have opened. This is a pygenin, like I mentioned. This is a ligand I'll be docking with my protein. Okay, to download this my ligand, what do I need to do? I need to scroll down to download the 3D structure of the ligand. You can download the 2D and the 3D, okay? But in most cases, 3D is preferable for docking, okay? So this is my 2D, this is my 3D, okay? I've got to my 3D. So what do? You can see this my 3D is in ball and stick form, okay? You can put it in stick, wireframe, and the rest, but it doesn't affect anything, okay? It's already in what 3D form, so you can leave it in this default form. By the right, you see your download button. So what do? You simply click on your download, okay? It will give you different formats of this PDB, this particular your ligand you want to download. I told us that ligands and proteins are usually downloaded in what? In PDB format. But as you can see here, there is no PDB format here. So what do? I'll have to download my ligand in SDF format and later convert it to what? To PDB via different softwares or tools, something like OpenBabel, something like PyMOL, and some other online servers you can use to convert different forms, okay? So I'm going to download this as an SDF file by simply clicking on my save, okay? As I click on my save, you can see by the down left side, it has already downloaded my what? My ligand, okay? So the next thing I do is to convert my ligand, okay? And then use it for what I want to use it for. Okay, you are welcome back. In this video, I'll be showing us how to convert our just downloaded ligand into a workable format. Okay, we just downloaded our ligand in SDF form. These docking tools or docking apps do not recognize ligands in SDF file, so it must be converted to PDB format. Okay, I've told us we use various tools to make a conversion. You can either use an offline tools like OpenBabel, PyMOL, and the rest to convert your ligand from SDF file or from another file to what, to PDB format, okay? But in this tutorial, I'll simply use an online server, okay, which seems to be faster, okay, and easier to use to make my conversion from my what, SDF file to my what, to my PDB format, okay? So what do? I will simply come and search for convert SDF to PDB, okay? Convert SDF to PDB. Click on enter, okay? And it loads. And this is the page you are supposed to find despite the browser you're using, okay? So all these can help you convert from one form to the other, okay? But for the sake of this tutorial, I'm going to be converting mine with an online smile translator, okay? An online smile translator. So what do? I'll simply click on it, okay? Once I click on it, it will load, okay? And this is the interface of my online smile translator, okay? This is what I will be using to convert my SDF format to my what, PDB format. So what do? If you look at this left side where you have your start structure editor, okay, and the rest, by the downside you see a choose file, okay? This is where you're supposed to choose your file. So once you click on the choose file, it's supposed to take you to where your downloads are, okay, or where you can pick the file or the format you want to translate into PDB. So what do? I'll click on choose file. Once I click on choose file, it will take me to my downloads, okay? This is actually the file I just downloaded, okay? I want to convert to a PDB format. So I'll click on it, okay? And I'll click on open. It has loaded it here, okay? This is it here. It has loaded it here, okay? So by the next right hand, it will tell you the different formats you want to convert it to, okay? Which format do you want to convert it to? I want to convert it to PDB, so I'll click on PDB, okay? It will ask me, do I want to use Kekule or aromatic? Kekule is fine, okay? Is it 2D or 3D? Me, I prefer 3D. You can work with 2D, but in most cases, we'll work with what, 3D. So I've finished my selection. The next thing I do, I'll hit on translate. Okay, it has translated my what, my ligand from SDF file to a PDB file. Okay, so what do? I'll click on here. You can see click here. This click here means to download the file format that be converted. So what do? I click on it. As you can see by my down left side, it have started downloading my converted protein, or my converted ligand. Okay, you can see that. So how do I locate where it is? I'll click on the arrow. This is just because of my browser. Your browser may have a different way you access your downloads, but this is where my downloads are fine. So I'll click on show in folder. So I will see where it was downloaded. So this is what I have here. Okay, this is the ligand in what, PDB format. So what do? I'll right click to rename it. Okay, I'll simply rename it to my ligand, which is a P-genin. Okay, I'll hit enter and it will be renamed. So I've got my protein, I've got my ligand. I am now ready to prepare them for my molecular docking. Thank you and see you in the next video. Okay, in this tutorial, I'll be showing us how we can prepare our different proteins or ligand before molecular docking. Okay, for the sake of this, I'm going to be using a tool we call Discovery Studio. Okay, this is the 2021 version. Okay, there are several other versions you can make use of, and they are easily accessible online, so you can download them and install them. Remember, there are other tools There are other computational biology tools you can use to prepare your protein, such as PyMOL and the rest, okay? But for the sake of this tutorial, I'm going to be making use of Discovery Studio. These proteins need to be prepared because some of them, due to they are downloaded in their crystallized structure, do contain water molecules and the rest, which our docking tools may not need, okay? So we need to clean some of this off and make sure our protein is free, okay, and prepared before molecular docking. Okay, to do that, I'll simply go to my file, open it where I've saved what I've downloaded, okay? I'll go to open. Once I click on open, okay, it will take me to where I can find documents, okay? This is under download, but what I have is under my desktop. So I'll click on desktop. When I click on my desktop, I'll go to my docking tutorials. That's where I've saved the protein and the ligand. This is the protein. This is 2-ACE. That is acetylcholine esterase. I've already downloaded it as explained in the previous tutorial or video. So I'll simply click once on it and say open, or I'll double click on it and it will open. So I'll open it. When I open it, it will get loaded into this place. Okay, it has loaded, okay? From what you can see, I'm working with a laptop, so I can't move this around. If I click and scroll around, I can only select it, okay? So I'll need to change the setting of my mouse by simply right clicking and coming to mouse mode, okay? I'll translate it to rotate, okay? If I can rotate my protein, okay? I can now rotate my protein. I can also change it to translate, okay? So I can shift my protein from one point to the other, okay? But for now, I prefer the rotate mode, okay? So I'll put it on rotate. As you can see, I have some dark red spots, okay? And then something at the middle, you can see this is the ligand, the internal ligand, the co-crystallized ligand, okay? It's always very necessary in our docking studies, okay? So that you'll be able to know the location of the active site and how the protein interacts with its internal ligand, okay? So simply what do we do to clean up this protein? As you can see, I still have a dark background. I personally like working with a white background. So I'll simply right click, go to my color, go to background, okay, and change my background to what? To white. And I'll click OK. And I have a white background, okay. You can now see the water molecules. That's this dot, this small dots, okay, red on the surface, okay. So what do I do? I need to clean them up. Where do I locate them? As you go towards your left, there is an arrow here, okay. Once you click on the arrow, the components of this particular structure will come out, okay. As you can see, this is just a single chain, okay. That is why I have only one chain A, and the ligand and the water. The first A simply represents the protein. If I click on it, it will highlight the protein, okay, telling me this is the protein, okay, the quaternary structure of the protein. If I click on the second one, if I click outside now, it will return to its normal structure. If I click on the second, okay, it will highlight just the ligand. As you can see, the ligand is now what? Highlighted, telling you that the second A stands for the ligand, okay. Then if I highlight the third A, okay, it will highlight the water molecule. Can you see the water molecules are now highlighted? Okay, so which simply means what these things represent here. So here I want to clean up all this. I only needed just the protein, okay, or the protein and the ligand as the case may be. Okay, so what do I do? To also confirm if what you have here is as A is your protein, you can easily click on this arrow by the end here, or you can easily unhighlight this. If you click on this thick grid, if you click on it, it will disappear. You can see the protein has disappeared, telling you that this A is actually the protein. That is the quaternary structure. If I click back, it will come back. Then if I click on the second one, the ligand will disappear. There is no ligand again here. If I click on it again, it will appear, okay. The same with water. If I unhighlight water, water will disappear. If I click it back, it will come back, okay. So I need to clean it up. Remember, if you're working with more than one chain, okay, you are supposed to have A, B, A, B, A, B, or if you have up to 3 chains, you'll be having A, B, C, A, B, C. That's how you keep cleaning up until you have just A in your structure, okay. So I will need to highlight on water just by clicking once, and I will use delete key to delete the water molecule. Okay, I will also click on my ligand, okay, and delete it. So this is my protein, okay, is my protein now. It's very, very free now. Okay, so I can save this protein. To save my clean protein, I'll simply go to my file, go to my save as, and it will come. Then it will ask me what name do I want to save it. I'll save it as cleaned, okay, cleaned protein. Okay, this is clean protein, but it's still in Discovery Studio file. No, I need it in PDB file. So under the name, the file type, I'm going to change it to what? To PDB, which is what? Protein data bank file. Okay, I'll click on it, and it's now in data bank what? File. It has already taken me to where I'm supposed to save it. Okay, but if yours didn't take you to docking tutorial where you're supposed to save it, simply what? Navigate your way to the file, and then simply what? Click on save. Okay, I'll click on save, and it has saved this my structure as a clean protein. Okay, assuming I want to save the ligand, internal ligand, I'll simply do Ctrl Z, okay, to bring back my what? My ligand. You can see my ligand is back now. So what do? I will click on the A, select the protein, and delete it. Okay, I have only my ligand now. Okay, so I can save my ligand as well. Assuming I want to work with internal ligand, I'll go to save as, okay, and then I'll save it as what? Cleaned ligand now. Instead of clean protein, I'll have clean ligand. Okay, is it a Discovery Studio file? No, it has to be in what? PDB file. Okay, so I'll save it as PDB file, and I'll click on save. And this is how I've prepared my protein and my ligand for molecular docking. Thank you, and see you in the next video. Okay, you're welcome back. Some people do ask, do we need to clean up our ligands after downloads? Okay, I will show us. Once you've downloaded your ligand and you've saved it in a PDB file, okay, a PDB format after your downloads, you don't need to prepare it again or clean it up again here. Ligand comes just as they are, okay? Once you download them and convert them to your PDB format, they are safe and they are okay for molecular docking. For instance, if I go to my file and I try to open my just downloaded ligand, okay, this is the ligand. If I open it, you discover that the ligand is just appearing very free. This is my ligand, okay? If I change this background to a white colored background, okay, you will see my ligand very, very clearly. Okay, this is my ligand, very clean. Okay, I don't need to clean any other thing here. Okay, and it's already saved as a PDB format. But in case you downloaded yours and you didn't save it in convert it to PDB file, okay, you can still use Discovery Studio to convert it to a PDB. Okay, that's the only case where you can make use of Discovery Studio to prepare your ligand, assuming you downloaded it in SDF file. Okay, you can open it up in PDB in Discovery Studio app or tool or software and use your file, save as, okay, and make sure here at this particular save type you change it to what? To PDB. Okay, once you change it to PDB, it becomes a PDB file. Okay, if you don't want to use the online server or many other tools like PyMOL and the rest. Okay, but here I have already converted my ligand to a PDB file, okay, in one of our previous tutorials, so I don't need to go further, in preparing this again. So this is ready for molecular docking. Okay, see you in the next video. Okay, welcome back to the tutorial. In this video, I'm going to be showing us how we prepare our proteins and ligand before molecular docking. Okay, as you can see, I'm making use of Autodock 2, okay, under which you have Autodock Vina. It's one of the recently used tool for molecular docking, okay, and is accepted everywhere, okay, because of its different features. So in this particular tutorial, we'll be making use of Autodock tools, okay, to prepare our proteins and ligand for molecular docking. Okay, to do that, we'll have to load our proteins and the ligand and then prepare them. What does it really mean to prepare these proteins and ligand? It's simply adding the necessary components onto our protein like charges and the rest, okay? Hydrogen, ion, our different bonds, we want them to reflect on what we're working on, okay? So to do that, first of all, I will have to load in my protein, okay? I'll load in my protein through my file. I'll click on my file, okay? I'll see read molecule, I'll see read section and the rest. I'll have to read molecule in order to be able to generate it, okay? Once I click on read molecule, it will take me to where my files are, okay? But my file is at my desktop, so I'll click on my desktop, okay? And I will locate my file at what the docking tutorials. So once I click on it, it will open. What I want to work on, I will work on my protein first, okay? That is this clean protein, okay? I just cleaned that with Discovery Studio, okay? So once I double click or click once and click on open, it opens, okay? So I'll double click. It's trying to load on my Autodock tool. Okay, as you can see, this is my protein, okay? I've loaded it here. Okay, the first thing I will do is to add a color to the protein. Okay, I'll click on this button here. As you can see, once I use my cursor here, you see something here, a display of color menu. Okay, I'll simply click on it and I will color this my protein by atom types. Okay, the different atoms in this particular protein will bear different coloring. Okay, I'll simply click on by atom type. Okay, and then I'll close it. Okay, as you can see, it has reflected on my protein. Okay, the next thing I do, I'll go to edit, okay, to add some other things, features I need on this particular protein before I subject them to docking. I'll click on edit, then I'll first of all add water is already deleted, so I don't need to delete water again. But in case you didn't prepare yours with Discovery Studio, meaning you still have some water molecule or whatever in your protein. So what do? You can delete some of them from here, okay? But our water is already deleted. So what do? We'll go to add charges, okay? You can add command charges and you can also add compute gangsters, okay? For the sake of this tutorial, we're going to be using compute gangster, okay? So I'll simply click on that. Okay, it will tell me total gangster charge added is this. I'll say fine, okay. It will add it, okay? You may not be seeing some of them, but it just added that. So you can go back to your edit. You are done with charges. The next thing is to add hydrogen, okay? Hydrogen is very, very necessary during this docking process. So I'll click on add hydrogen. It will ask me, do I want to add all the hydrogen or polar hydrogen? I don't need all the hydrogen. It will make the structure too wide and big and so ambiguous too. So I'll simply click on what? The polar hydrogens only, okay? The polar ones are the ones required or necessary for interaction. So I'll simply go on OK, okay? Yeah, as you can see, just reflected on the structure. I've added my hydrogen, I've added on my charges, okay? The next thing I do is simply to go to my grid, okay? I'm done preparing this protein. I'll go to my grid, go to my macro molecule, okay? I want to save the prepared protein. I'll go to choose molecule, okay? This is the molecule I'm talking about, which is my protein. So I'll simply choose it and click select molecule, okay? Once I select molecule, it's supposed to take me to where I can save this particular protein, okay? It will tell me initialize this contains no non-bonded atoms. Yeah, if this kind of box didn't come out, it means your preparation wasn't correct. But as you can see, I have no non-bonded atom, meaning all my atoms are what? Bonded. So I'll tell it, okay. then it will take me to the file where I want to save it. Like I always say, I have my file or my folder at the desktop, so I'll have to go to my desktop, click on desktop. It will bring me to here. Look at where my file is. I'll click on my tutorial. Okay, I will open it, or rather double click it. It will open whichever way. Because I don't have this format yet in the file, it will show an empty item here. This file is in what? Is in PDBQT file. Okay, that is the output file of any work done on what? An Autodock 2 app. Okay, it has to be in this PDBQT. If not, the command prompt will not understand or will not read this molecule as a protein. Okay, so in the PDBQ format, we simply say save. Okay, and we have successfully saved our protein for molecular docking. Thank you and see you in the next video. Okay, you're welcome back to the tutorial. In a previous video, we just prepared protein for the molecular docking. In this video, we are going to be preparing a ligand for molecular docking. Okay, to do that, I will simply go to my left side. Under this, you see an option for ligand. Okay, I'll simply click on that. So when I click on ligand, you will see some options here. You see input, you see torsion tree, you see this, you see that. So I will first of all input my ligand by going to open. Okay, it will take me to the folders where my documents are. Okay, I will navigate to desktop where I saved it. You can see docking tutorials. That's where my files are. I will click on that. It will open. Okay, as you can see, I can't find all my files here, so I'll have to change the file type to what? All. And once I do that, I can navigate through all I have saved under this folder, among which is my ligand, the arpeginine. Okay, I'll simply click on that, double click to open, or click once and open it here, and it will load into my workspace. Okay, it will bring out this option for me. Usually I'll tell it yes, just okay this. Okay, and you can see your ligand here. So this is your ligand. So to prepare the ligand, I will go back to my ligand. I'll go to my torsion tree. Okay, I'll need to dictate roots. Okay, you do what? You dictate the roots. Okay, as you can see, it just reflected on your words, on your ligand. That's this point here. Okay, after that, I'll go back to my ligand. Okay, through the same torsion tree, I'll go and choose some torsions where I want this particular ligand to, interact with my protein. Okay, as you can see, these are the different torsion trees I can generate for my ligand. So I'll just say done. Okay, then lastly, I will go back to the same ligand. Then under the same torsion tree, I will go to what? Set number of what? Torsions. Okay, as you can see, 4 different numbers of what? Torsions has been generated here. So I'll simply say okay, dismiss that. Okay, as you can see, I'm done preparing my ligand for what? For molecular docking. So I'll simply go to the same ligand in order to what? Save my output. I'm done with the preparation. So the next thing is to save my output. And note, it must be in form of what? A PDBQT format. Autodock Vina, which we are going to be using for the docking process, don't recognize every other format for docking except what? PDBQT. So one of the reasons why you prepare this is to also save it in what? In PDBQT format. And once you save that, then the Autodock Vina for the docking process will be able to recognize that. So we simply click on what? On save. And it's supposed to take us to our folders, okay, where we want to save it to. I will still go to my desktop. Then I'll go to my docking tutorials, okay. I can save it here, okay. So I'll simply click on what? Save. And once I've saved it, it's now found in my what? In my folder. So every other preparation has been made, okay. So the next thing I do is to simply prepare my config file, and then I'm good to go with the docking process. See you in the next video. Thank you. Okay, you're welcome back to the tutorial. At this point, we'll need to generate some grid setup or option for the docking. Okay, we've already prepared our protein and our ligand, but we need to generate some grid setups, okay, or option from the protein, okay, that will enable our command, to actually perform the function we want them to perform. Okay, to add grid setups, we'll simply go to our grid. Okay, you can see grid option under the ligand row. You can see grid. Simply click on grid. Okay, it will ask you to open this. No, we'll go to our what? Our macromolecule. Okay, and now open it. Okay, if you open it, this is where it takes you to, but mine is on my desktop. So I'll go to my desktop, my docking tutorial. Okay, I'm supposed to add the grid setups towards my protein. Okay, that is the options where I want the ligand to be located. Okay, or where I want the docking to occur. I'll need to indicate it through my grid setups. Okay, it has to do with options and numeric numbers. Okay, so I'll simply go to my protein here. As you can see, it's already in what? In PDBQT format, meaning it has earlier been prepared using this particular tool. So I'll just select the protein and I'll open it. It will ask me if I want to retain all I've already prepared about this particular protein. I'll tell it yes. Okay, I'll go ahead and say yes, and it will load in my protein. Okay, for me to do whatever I want to do with it. Yes, it will still give me this option, say this, and then ask me that this actually contain no non-bonded atom, which is fine. I've already prepared that for this before. So I'll say okay. Then this is my protein from what I prepared before. Okay, so what do? I just need to add few grid setup, and like I said, it's just targeting or trying to position your protein in such a way that the ligand will be directed to a particular portion for what? For docking. Okay, where the ligand will have to locate itself during the docking process. That's simply what we want to add now. If you don't do so, the ligand will have a way of just binding to any portion or any side of the protein without locating the active site or where you want it to bind to. And it's at this particular point that if you have a site directed or site specific molecular docking, it's at this particular portion or time that you do what? You confer those features or put in those options in your protein and allow the docking to occur at your own preferred portion or preferred pocket. Okay, to do that, I will simply go to my grid. Okay, I've already opened it, so I'll go to set map types. Okay, set what? Map types. The map is where you want the docking to occur. Okay, I'll simply set it what? Directly. Okay, if I click on set directly, it will tell me, do I want map type this? I will say yes, I will accept it. Okay, these are default commands. Okay, the ones you need to accept, you just accept it and it will be done. Okay, so I'll still go back to my grid. I've already set my map types. Okay, then the next thing is my grid what? Box. I'll click on my grid box. Okay, once I click on my grid box, something has appeared here. Okay, can you see that? Something has appeared here. This thing that appeared here is where the ligand is likely going to bind to. Okay, that is the pocket where the ligand is going to bind to. If you want to edit anything here, okay, all these knobs here is movable. Okay, can you see that? The more you move it, can you see as it's affecting the structure of that inside? Can you see that? Okay, so I have 40 here. I'll just make use of the default setup, okay, which is 40. This is what I have, except I have a side directed docking, okay, where I have a specific amino acid I want the binding to occur. Then I can make use of that. But aside that, I can just use the default setup as generated here. Okay, so this is the default setup. Before you close this setup, it's always important you save these options here. Okay, because you'll be needing this while preparing a file we call the config file. The config file is still going to be part of the docking material, okay, that your system is going to recognize before docking is done. Okay, so what do? I'll go to this file and I will save output grid dimension file. Okay, I'm going to save it. I'll locate where my file is. This is where my file is. I'll open it. Okay, and then I will save this as grid file. Okay, I'll save this as grid file. This is my grid file. Then I will just click on save. Okay, and I have a copy of this information saved on my file. Okay, in case I use it for another thing else. Oh, so simply I'll just go to my file again and do what, and close without saving. Okay, I've already got that done. Okay, that's all. The next thing is simply to save my my grid option. Okay, I'm done preparing the grid setup, so I'll simply go to my my output. Okay, I've done the grid box. I'll simply go to my output and do what, and save it as GPF file. Okay, I can click on that and it will take me to where my documents are. I'll simply go to my desktop and go to my tutorial. Okay, I can label this as grid option. Okay, and if that is done, I'll click on my save. Okay, as I've done that, I've saved my my option. Okay, remember, while saving the grid option, you have to go to grid, go to, sorry, while adding your grid box. Okay, after you add your grid box, when this appears, okay, when you're done saving the file dimension, okay, you simply save. To close this, you save without what, you close without what, without saving. Okay, you don't need to save, close saving current days, just close without what, saving this way, and it's closed. Okay, and you are done with that. So this is how we prepare our files, our protein, our ligand, and our grid option for what, molecular docking. All are ready now. The next thing is to perform your molecular docking. Thank you, and see you in the next video. Okay, you're welcome back to our tutorial videos. Okay, in this video, I'm going to be showing us just one remaining step before our molecular docking. Okay, we are done preparing all we are working with, our proteins and ligands. Okay, but we are here to prepare a particular file, very necessary for the docking process. Okay, we'll call this file the config file. We'll call it what, the config file. This is a file that, you know, summarizes all you've prepared, okay, and how you prepare them. Okay, the different coordinates, the protein, the ligand, and all the rest you are about to dock. Okay, an example of a config file is what you're seeing on my screen now. Okay, this is an example of a config file. Okay, if you look at it, I opened this through a notepad. Okay, you can make yours, or you can design yours, or write your config file in a word pad. Okay, it mustn't be a notepad. So you simply open your notepad or your word pad and type exactly what you can see on my screen. Okay, the first one is your receptor. After typing your receptor, you hit your space bar button on your laptop or on your keyboard. Okay, and type equal to, and then hit space before typing the name of your protein. But in this case, I will not recommend you to type the name of your protein. Okay, there is a way you are supposed to copy and paste it so that you can easily not make a mistake. Okay, so don't type it with your hands, but rather do copy and come and paste it here. I will show you how you do that. Okay, so these are what we have here. Then we will go back to what we just prepared. Okay, so this is the docking tutorial. This is the file where all I have prepared for docking is located. Okay, so I'll simply open the file. Once I open it, this is what I have. This is my clean ligand. This is my clean protein. Okay, this is my prepared protein for docking. This is the original protein. This is my ligand. This is the prepared ligand for docking. You can see it in PDBQT format. Okay, then this is my grid file, and this is my grid option. Okay, when I was preparing my grid setup, I saved the file. Okay, if you remember, this file I saved is what contains all the coordinates for this my molecular docking. The target where my ligand is supposed to bind to my what, my protein. I've already set it. So that is where I'm going to open, okay, to get some details I will use for my config file. Okay, but I already have the detail, the name of my protein, and then the name of my ligand here. Okay, I will first of all copy these two before opening my config file. So how do I do that? I'll simply tap on this and tap on it again. It will show me as if I want to rename it, or you can click outside, tap on it, and then right click and go to rename. Okay, click on rename. It will highlight it this way. Then you can easily highlight everything, okay, including the PDBQT. Okay, after highlighting, then you control C or copy it. Okay, and then go to your config file. This is your config file. For the receptor, it means the name of the protein. So you simply do what? Paste it. Okay, you can see now you now have the name of your protein here. Okay, then we're looking for ligand now. I'll still go back to my file. Okay, this is my ligand. Then I will copy it, and then I will go to my part, and then use it and replace my ligand here. Okay, I'm done with my ligand and my protein. I've told you, if you're typing this for the first time, after typing your receptor, put a space, type equal to, put a space, and then paste the name of your protein in PDBQT format. After typing ligand, give a space, put equal to, give a space, and then put in the ligand you're working with here. Okay, then these are the coordinates. We have x, y, and z coordinates, and we have size x, y, and z. To get this now, we'll have to open our grid file. Okay, we prepared during our grid option, okay, or during our grid box setup. Okay, I'll simply go back to my file and open the grid file. It will ask me what do I use to want to open it. Okay, I can open it with my notepad. I'll say okay. Okay, as you can see, let me minimize so that you see it. Okay, as you can see, let me minimize this. Okay, I can minimize the two on my screen now. Okay, you can see that. So this is my grid file I saved after preparing my grid box. Okay, and this is my config file. Okay, I can place them side by side like this and copy and paste. Okay, I've already copied my protein and my ligand. It remain my coordinates. The x coordinates, if you go to your grid file which you saved, this is the protein, this is the spacing. This NPTS simply means this size x, y, and z coordinates. Okay, this is the 40 40 40. So I have 40 already here. Okay, but during your own, you still type the same thing and do what, and put 40 40 here if you're making use of 40 as your xyz. Okay, remember, while typing these coordinates, this is underscore, not just a semicolon here. This is an underscore. After typing C, you put an underscore before S. If you don't put an underscore, this command will not recognize this your file. Okay, so I will simply edit my center X, Y, and Z. Okay, my center X is 4.787. So I will simply copy that Okay, I'll copy it and then I'll paste it here. Control V. Okay, the same thing, I'll copy this. Okay, then I will come here and paste it. Control V. Then I will still copy this. You can copy by simply clicking on Control C. Then I'll come here and paste it. Okay, this is what I have. Then it's already in my size X, Y, and Z is 40, 40, 40. That is what I want to work with, the default size. Okay, then this is my output. Okay, this is my output. How do I want it to appear after my output? I always leave mine in Ligand all. Okay, Ligand all in PDBQT format. Okay, don't worry, when our result is ready, you will see it. So your result will appear as in a Ligand all in PDBQT format. If you want another one, maybe you want yours to appear in Ligand or in all result. Okay, just type it and put it .pdbqt. It must be in .pdbqt format. Okay, so this is how you prepare. I can now close this. So this is what I now have as my config file. Okay, so I'm supposed to save this file to the same folder where I have other of my documents or other of my preparation. So what do? I'll go to file, I'll go to save as. It's already as a config, so I don't need to edit it. So I'll locate where it's on desktop now. So my files are on tutorial, docking tutorials. So as you can see it here, I'll simply click on save. And I've saved it to that my file. So I can minimize, okay, and go and open my file. Once I open it, I'm supposed to have my config file. So this is my config file. So I now have all it takes to perform a molecular docking now. And the next thing I'm going to be doing is the docking command. And you see how it's done and how the result is being generated. Thank you, and see you in the next video. Okay, you're welcome back to tutorial. In this particular video, I'm going to be showing us how the docking commands are being performed. Okay, you finished all your preparations, you saved them in the right format, you want to perform the molecular docking. Is at this particular point that you queue in your different commands, okay, and your molecular docking process will commence. Okay, what do we simply do? What I'm using here is a command prompt. Okay, or a DOS as some people may call it. It is a command prompt app. You can easily open it or search it from your button, okay, from your search icon. This is my command prompt I just opened. Okay, so once you open your command prompt, this is the interface you receive. We simply use command prompt because we want to locate the different directories and files, okay, or softwares we're supposed to use for this our docking. So what this app this does, or command prompt helps us to do, is to what, to navigate to our different folders or files where our different softwares for this docking is located. So to commence that, I will simply write cd, which is change directory. Okay, I will click a space button. Then I will go to my file and simply copy my path. Okay, this is the file where I saved everything I want to dock now. Okay, these are all my parameters. My parameters are already prepared. So I'll simply tap once. As you can see where I place my cursor at this directory format, this directory option, I'll just click my cursor there, just a single click. Okay, and you will see this title here, what, highlighted. Okay, I'll simply right click on it and copy it. Okay, I've copied the directory to this my documents now. So I'll go back to my command prompt and then I'll just as you can see, it's still blinking from the CD. I just type CD, which is change directory, and then space button. I'll simply right click, okay, just a right click, and this will appear. Just what? A right click, and what you have here will appear, what you just copied. Okay, this is command prompt, and this is how it works. So I'll simply hit my enter button, okay, and it will bring me to this. It has already located my directory now. Okay, so what do? I simply want to now give it more commands to locate where my file is. Okay, so I will start my command by a inverted comma, okay, and then I'll use my backspace, my backslash, and then I'll type my P, okay, an inverted comma, a backslash, and a P, and then I'll use my tab key. Okay, I'll be hitting on my tab key until I locate the file where my docking app is located. Okay, I'm just trying to navigate to where my softwares and my apps are. Okay, so after typing inverted comma, a backslash, and P, which is the path, I'll simply tap on my tab key on your keyboard. You see a tab key until you get to a program file h6. That is where I installed my own what software. If you trace your file location, you have to go through your file location and know where your file or your app is installed. Okay, mine is in h6, is in program files h6. Okay, once I've got this, I'll click my backslash again. I want to open that file. Okay, let me see what is inside it. So I will use my tab again. Remember, you just type your backslash, just a backslash, and use the same tab again. You'll be looking for your file, you'll be looking for it, okay. As you can see, mine is going, I'm looking for it. Okay, this the script research institute is the file, okay, I'm looking for inside this program file. Okay, I've got that. Then inside this research script research institute, that is where my Autodock Vina, which I'm going to be using for this docking process, is located. So what do? I'll type my backslash again and type a V, which is the Vina, okay, the Autodock Vina I want to make use of. And then I'll hit on my tab key again. Can you see I've located my Vina inside it? Okay, I've located Vina, but I need Vina.exe also, okay, inside the same Vina. So I will simply type my backslash again, just backslash, and I'll hit my tab key, and it has located what? My Vina.exe. Okay, this is what I'm supposed to use to make this command possible. So I'll simply hit on my enter button, and this is what is generated. Okay, once you generate this form, you can easily hold down your center key, your enter key. Okay, just hold down your enter key to give your docking a bit space. Okay, I just hold down my enter key and it gave me a particular space. Okay, so once it gives you this space, the next thing you do, in your keyboard you will see the arrow buttons. You have about 4 arrow buttons. Okay, just to bring up the last command you have up, simply use your arrow command, the upper arrow command. Okay, just hit on the upper arrow command and this thing will come out. Okay, then I want to tell this particular command now. I've located the software, the app. Now I want to tell it, what do you want to do for me? Okay, you're supposed to perform a molecular docking work for me. Okay, so I'm going to tell it which file is going to dock for me and where my output is going to be located. Okay, so to do that, I will simply hit my space button 1. You hit your space button 1, then you type a config. Okay, that our config file we've prepared at the process of before this molecular docking. If you haven't watched that video, simply refer to the previous video where we prepared our config file. That is where all the content we want to dock is located. So this is my my config. Then I'll hit on spacebar again and then put my config.txt. Inside that config, the config is in a txt format. Okay, so that once it locates config, it will what? Sorry, as you can see, I didn't type the config very well. So I have config.txt. Remember, once you make, even if it's a single mistake here, a space mistake or a typographical error here, the whole software will not recognize it, okay? And you will not be able to perform docking again until you have to restart everything again or trace where your fault is located, okay? So I've typed my config file. This is the file I want it to pick and dock, since all my information is there, including the site for docking, okay? I've already typed my config and my config.txt. The next thing, I'll hit my space bar and then type where how I want the output to look like, okay? The output is going to come out as a log file, okay? So I'll simply hit on my word as I'm going to type my log file again. Oh, sorry, remember. Okay, let me type this again. We escaped something, okay? We escaped something. Just clean up everything again, okay? Clean up everything again and start again with your space bar. Then, first of all, before you type your config, put this too, okay? That's your dash button, okay? Hit on your dash button twice, okay? Your dash button twice, or hyphen, okay? Hit on your hyphen twice before you type what? Your config. This is simply a command prompt language, okay? Config.txt, okay? Then I'll hit on my space again, hit on that slash again, or that hyphen, okay? It's simply telling you locate this file, and you have to pass two files before you locate the config, okay? It's just as simple as that. That's what we just indicated now. So I've ticked on my hyphen again twice. Then I will type my log space bar log.txt. Okay, so I finally generated the software I'm supposed to use to dock, which is my Vina .dxt. That is my Autodock Vina, like I told us, and the config file where my files are located, where all I'm supposed to dock are located, and then my output file, which is what? My log file. So I'm done preparing this for molecular docking now. The next thing is just to hit my enter button, and my docking process will commence. Okay, so I would simply hit on my what? My enter. Once you hit enter file, your enter button, the reading for the docking will commence. As you can see, it's already analyzing certain things. Okay, for me, the reading is done. The setting up for the scoring function, as you can see from your down left end, is done. Is analyzing the binding site now from the location I gave it, from the description in my grid setup or my grid box option. It's trying to locate where my active site is now, or where my binding site is. As you can see, is reading it. Okay, as you can see, it has started what? Docking. It has started docking. It has started docking. Okay, it has started docking. It has started docking. As you can see, some of them will take some minutes, some of them will take some hours, some of them, no, it doesn't take up to hours, depending actually on the size of the protein you're working with. But most of them depend, and also on the fastness of your system. Okay, if your system is not too fast, it may not really take it very, very fast. Okay, so as this is running, I will just in a bit show us what these commands we just inputted now are again. Let me make use of this. Okay, I can clean up this. Okay, so I can show you again. I told you simply the first thing you do is to type your CD. Okay, once you open your command prompt, type in your CD. Okay, then space. Okay, CD, then space. Okay, that's by hitting your space bar. Then you go to your directory. Okay, where you saved all your files, okay, and simply hit once on it, okay, and then copy it by right clicking and copying it, okay, and then you go to that same command prompt and what? Post it. After that, your CD, just by clicking your right button, okay. So I will just say space, then copy your directory and then hit right key on your command prompt. Okay, once you hit that, type your space or hit your space bar, then copy your directory, then hit the what? The right key on your command, and this directory will comment. Then you can now start with your remaining commands, which is semicolon /p. Okay, you use your tab key. Okay, then use your tab key. Okay, after that you locate your file, then you also click again your slash. Okay, and then use your tab key again. Okay, I'll use my tab key again. Okay, okay, let me put it this way. Let me put this in enter. Okay, so this is what I have. Then space. Okay, after using the tab key again, the next thing you do is type /v. Okay, then use your tab key. Okay, the next thing you do, you type v. Okay, and then simply hit on what? Then hit enter. Okay, then hold down your enter key to give your docking some space. Okay, then after, click up arrow. Okay, to recover your path again. Okay, then after recovering your path, the next thing is to type in where you want it to locate the file and where your output will be found. So then type, okay, let me space this again, then type what? Okay, you type again this and then log.txt. Okay, so this is what you have. Once you're able to enter this command in your command prompt, you then hit enter. Okay, and docking starts. Okay, so that is how you perform molecular docking. I'm sure by now, just notice this or hold down this or go through this very well and you see how it's done. Okay, and compare it to what you have in the video. So if you go back to what we have commanded in our prompt, is supposed to be done. Okay, our docking is already done, and you can see this is our result. Okay, this is our different affinities and energies. Okay, this is the distance from the RMSD. Okay, this is the best mode RMSD. Okay, we have all this, but this is one of the most important items we're looking for, which is the binding energies. Okay, on affinities. So you have seen how we perform the molecular docking, and our results is generated now. So if we go back to our file where all we have done are located, you will see that we have generated what? A log file because of our command. This log file is the output. If I open this file by double clicking, okay, it's supposed to open. This is the file, okay, and this is the same result I have in my doc. my command prompt. Okay, this is simply the file. Okay, and this is the result. So I'll have this result on my what, on my output, and it will be there anytime, anywhere, any day. So this is how we perform molecular docking using our command prompt to enter in the commands, whereas the app we use for that is our what, Autodock Vina. Okay, thank you and see you in the next video.
All right. Thank you so much for joining us in our today's class. In this video, I'm quickly going to be guiding us through the few post-docking analysis you carry out following your molecular docking. Of course, before now, you should have noted that few of the reasons why you perform molecular docking is to enable you, firstly, find out or investigate the binding pose of your ligand within the active site of your target or your protein. This ligand, of course, is your drug candidate or a compound you're investigating for potential drug. All right, so your ability to investigate the binding pose of that particular ligand within the active site or binding pocket of your target protein, all right, is what you need to investigate after the molecular docking study. That is what we call post-docking analysis. This is, of course, in addition to the binding interaction. Of course, after the binding pose is the interaction of the same ligand with the active site residues of your protein or your target. And lastly, the binding affinity, of course, the binding energies, all right, of the same interaction. So immediately after your docking study or your molecular docking using whatsoever tool you made use of, the next you should do is being able to interpret or investigate or even visualize this docked, all right, study. This is to guide your interpretation of what actually happened, all right, of what you think will happen in real life when such ligand or compound or synthesized product is finally developed into drug and all that. So we'll quickly go into that in order to save us some time. All right, from what we can see on the screen, this is a molecular docking I just concluded using Autodock Vina. If you are yet to know how to perform molecular docking, I guess you should refer back to videos, go to our playlist and find out videos on molecular docking, as well recorded videos on stepwise docking commands using command prompts just to get to this level I am in our previous video. So you could go back and make sure you get updated before continuing this video. So this your molecular docking has been completed. As you can see, this is about the 1 to 9 different poses or conformations of your ligand within the pocket of your target or of your protein. So that is what you have here, including the RMSD values and all that. So immediately after your molecular docking, if you return to the docking folder or the folder where you're working from, where you have your ligands, your target, and other your config file, that's if you're using Autodock Vina to dock. All right. So if you're using Autodock Vina, immediately immediately after your molecular docking, two extra files will automatically be added into your docking folder. Let's quickly go and find out about that. So I'll minimize this and then I'll go to my downloads. That is where I have my, this is my file, all right. This is the folder I was docking from. As you can see, this is the day I'm recording this, and this is the two files that have been added to my working folder. The first file is the log file of your binding affinities. If I open the log file, you will discover that I have the binding energies. All right, this is the exact binding energies you have from the command prompt software or interface we just concluded with now. So these are the binding affinities, of course, you are to report in your study as well. And then the first one is the 9 different conformations or poses of your protein, of your ligand within the active site of the protein. So we usually call it the protein ligand complexes. There are about 9 of it, corresponding to the 1 to 9 different binding energies we just found out in the log file. But as you can see, this is in a PDB-QT file, all right, and not a PDB file. So you might not be able to quickly view it with just any software. All right, so we need to find out what these conformations are like, and we'll quickly do that now. So to get that done, we'll have to go to another software called PyMOL. All right. For many of us, there are, of course, free versions of this, academic versions of this that you can access to enable you perform this. All right, so this is the PyMOL, which I've loaded here. Quickly, I will go to the folder or file where I have my results. And to do that, I'll go to my file. Please remember, if you are not yet familiar with some of the parameters you have here or the buttons you have here, you can quickly
Okay, you're welcome back to the tutorial. In this particular video, I'm going to be explaining to us how you can customize your 2D or 2D diagram view of your interaction, which is between your ligand and your protein. Okay. In a previous video, I explained how you can generate your 2D diagram, from your docking results. Now, after generating it, how do you customize it for some purposes like publication, okay, and some other places or things you may want to do with the image in order to make the image look more visible and more understandable, okay, or more presentable, okay. You got to customize the image generated. Cool. So how do we do that? I'll do that by simply loading in my protein. Okay, I'll load in my clean protein. Okay, then it has loaded. As you can see, this is my protein. Okay, if your mouse can't rotate yours, simply change the mouse mode to rotate by right clicking and changing the mouse mode to what, to rotate. Then this background, I love it to be white, so I'll simply go to my color and go to my background color, and I'll change my background color to what, to white, and then I'll okay it. Okay, so this is my protein. Okay, I want to insert the ligand inside, so I'll go to my insert file, go to this my file. Okay, then assuming I want to insert the second conformation of the ligand, remember the docking process generates up to 9 or more or even less different conformations of your ligand. So I just saved 2 from my previous video. I can use conformation 2, you can use 1, whichever conformation. I'll simply open and it will insert it. Okay, this has been inserted. You can see my ligand here, it has been inserted. So to generate the 2D image, like already explained, you come this way and click on your show 2D image. Okay, the 2D image is being generated. Okay, as you can see, this is just the default setup or the default view of the image. Okay, we need to customize this a bit. Okay, so how do I do that? I do that by simply right clicking, and I will see on display style. I'll simply click on display style. Okay, and this will come up. I have a general setup. I have for atom, I have for residue, and I have for interaction. Okay, so I can play around any of these here. Okay, so the first one is show legend. Okay, show legend is these items here. Okay, this definition of colors here. Okay, this interaction and their definition. So if I don't need it, I'll just unhighlight it. Okay, and it will go. Then I have a white background. If I want to change it to a different background, I can change here by clicking on it and picking my background. So I still like the white background, so I'll leave it in white. Then this is Cabri. This is the default uh, uh, writing type or font type of this write-ups here. Okay, if you want to change it to something else, you can. And then this, you can still edit that. So here is okay for me. Then I'll go to my atom. Okay, my atom is in line. Okay, if I don't like line, so I will change it to another thing. Okay, I'll change it to disk. Okay, and anyone you change and you click, you hit apply, you see it reflected here. Can you see stick? Stick is still not fine for me, so I don't need stick. So I'll see, and you can see the labeling have gone from the one I did here. Okay, so anyone you do and you hit apply, it will reflect. So I'll change this to stick. Okay, and I'll apply it. Let me see. Okay, I love stick. Okay, this is stick and it has shown me here. I like that. This is fine for me. Okay, then I will go to my residue. Okay, if you don't want this, there is some shadows you can see sometimes revealing where solvent accessible solvent is. If you don't need it, you can simply unhighlight it. Okay, if I highlight it back and apply, okay, you can see something like this now, something like this. If I remove it, okay, just notice what will happen here, and I apply it. Okay, you can see some of them has gone. No, this one is a bond, this one will not go, this one is a bond also. For some other surfaces that usually surround your edges here, like water, okay, you can easily remove it. It's not fine. Okay, so I used to remove mine. The same if you go to residue, you now be talking about this particular amino acids. Okay, the residue are in ball. I don't usually like ball. I can use stick. Okay, if I hit on stick and hit and apply, look at what it has changed it to. Okay, and then these are my ball size. Okay, you can increase this size to say 1. Okay, if I apply, look at how the size has become very big. So this is too big. I will take it back to 0.65. Okay, and then I will apply. Okay, it has become something like this. Can you notice that? So this is what I have. Okay, and many other, the interaction, you can also alter the interaction, alter some of this thing. Okay, look at another solvent area with respect to this particular residues. You can still highlight it. You can see the color here, and if you apply, the thing will go. Okay, as you can see, this with respect to this now, if I apply this, you can see something like this now, like I earlier wanted to show you. Okay, this is with respect to what, to this particular amino acid. If I don't want this to show, which I don't want, okay, they are not strong bonds, so I'll simply highlight this solvent accessible surface and do what, and apply it, and that thing will go. So this image is fine by me. Okay, I think I'm done with that. Okay, I'm done with that. I'm done with that. Is there any other thing you may want to add? Okay, then in interaction, do I need anything to add in interaction? No, I don't really need any. Okay, except you want to add whatever you want to add here. Okay, another thing here is show distance. Okay, if I click on show distance and click apply, very important, you will see the different bond lengths. Okay, this from this now is this size, this from this is this is the bond length from this amino acid to your ligand. Okay, in case you want to display the bond length, you simply click on this and then you apply, you are now okay. So I can say okay, but if you don't want to display the bond length, you can easily what, highlight it. Okay, and apply. Make sure you apply after every change you make, then you click OK. So look at the structure I've generated from my default structure. Can you see that this is fine, this is presentable a bit more. Okay, so you can use this for your publication or for your PowerPoint defense or whatever. Okay, so this is how we customize our 2D diagram for a different purpose, okay, using Discovery Studio software. Thank you and see you in the next video. Okay, you are welcome to today's tutorial. In this tutorial, I'll be explaining to us and also introducing us to one of our computational biology tools, This is PyMOL, okay? And we use PyMOL for several activities, okay? Especially as it has to do with visualization or alignment or some other functions you may want to perform, okay? Or even interconversion of formats, okay, of compounds or protein. So in this particular video, I'm simply going to be introducing us to the interface of PyMOL software, okay? I just loaded in my PyMOL. If you do the same, this is an icon of PyMOL, okay? And once it loads, this is what you see. Okay, towards the top, you see your file. Your file simply represent what some functions like save, just like in many other softwares you have your file. So here you can either use new as mean you want to create another page, a second working space for PyMOL. You can create a default working space. Then you have open. Open is when you want to load in your compounds or your protein into the PyMOL software. You use open. Once you click on open, it takes you to your folder and you pick the folder you want to interact with here, or the protein or the ligand in the folder you want to make use of. Then you can see open recent files. Okay, you can go to open, assuming you have opened them recently. Okay, get PDB. You can directly from here sort your PDB what online and the rest. You can save session. You can save session as. You can export your your alignment. You can export molecule. Okay, assuming you want to save a complex, you can simply save a complex and export it as what molecule and interact that complex in another software. Okay, you can also what export alignment. You can perform alignment with this among the functions it does. Okay, this is export images and export movie. You can create short movies using this software too. You can what also export your images after working or after visualization. Okay, you can simply what export your what image either as PNG or as any of these, but PNG is always what the most preferred. Okay, when after working, you export your file as what as PNG. You can also edit few things. You can also build few things. You can also, this is where you can create your movies and the rest. You can also affect your display. Under your display, you have your sequences, your sequence mode, and the rest. Among others, you have your background. Okay, this is where you change the background of your working space. For instance, I don't like black. I want to make it white. I'll simply do what? Click on white here, and the background change to white. Okay. So this is what you can do in your in your display. You can also visit your settings for some other activities you may want to perform with that. Okay, this is what you get used to with time. Then by the right hand side up, we also have few sections here. Okay, among which is reset, zoom, orient, draw, unlock, unpick, deselect, rock, and the rest. Okay, one of the most important here, which we make use of in almost all our workings on software, is this zoom option. Okay, once you click on zoom option, you will see zoom all, you will see zoom visible, you see zoom active selection, and you see zoom ligand, zoom next to ligand. Okay, when you're working on something here, you either make use of any of this to interact or to visualize what you are working on properly. Okay, if you want to bring it closer, either the active site, which is where the ligand is interacting, or you select some portions. I want to visualize the section you just selected properly. You can use on zoom active selections and the rest. Okay, don't worry, in our next video we'll be working on proteins and ligands, and you see how we apply some of these tools. Okay, under that we see this particular tool bar here. The first one I have here is A. A simply means action. Okay, if I click on action, it's telling me certain action I can perform with respect to what I have on this space. Okay, assuming I've loaded in something here, I want to perform an action. This is where I perform my action. And once you load in your protein and your ligand, it will also be recorded here. Okay, you see them record something like this here also. So this is my action. If I go to my action, I can zoom, center, origin, precept, and many others. Don't worry, in our next tutorial, you're going to see how we employ this in, while working with proteins or ligands. Then after action, I have my what? My show. S stands for show. Show means how do you want to visualize the compound or the protein you have here? Do you want it in ribbon form, cartoon form? Do you want to label? Do you want surface view and the rest? Okay, this is where we generate that. Okay, we also have what? H. H stands for hide. If you want to hide any of those things you showed, okay, at S, okay, S is for show, H is for hide. You can hide everything. You can hide wire, you can hide line, you can hide everything. Okay, just like you showed them here. Then the L here is label. Okay, do you want to label any component of what you have here? You want to label any residue, any chain, any segment, and the rest. You can easily do that via what? Labeling. Okay. Then the last one here is what? Is color. C. Do you want to color? Is it by element, by chain, by SS, by REP, by spectrum and the rest, or through any of this color, any of the color you generate here? And as you can see, once you click on them, you see some other section. Okay, any of them you select here and click, it will reflect on the color of what you have here. Okay, then lastly, we have this particular option here. Okay, these are different arrows you can use to move, assuming you have your protein and you have your ligand inside your protein. Okay, this particular option here helps you to get the different conformations of your ligand in your protein, assuming you have a ligand, a protein with different conformations of ligand. Okay, maybe after you just docked or performed molecular docking, you want to visualize the different conformations of the ligand in the protein. You simply load in the protein here and load in the ligand too, and use these arrows here to interact with them by clicking next or clicking backwards. Okay, and you see the different conformations of this protein, this ligand inside the protein's active site. Don't worry, you will see more of this. We will start our next video, or we'll start applying them in our next video. You can see this is S, where you can perform alignment, sequence alignment after loading in your proteins. Okay, and the rest. Okay, so these are just a quick summary of the interface of what PyMOL, okay, and what you can possibly do with it. When you start working on proteins or ligands, you will see how we employ this, okay, in a better way, and you come to appreciate it the more. Remember, I told you can perform several functions with this particular software. Okay, it's not limited to what I just mentioned. The more you make use of it, the more you find out about more of them. Thank you, and see you in our next video. Okay, good day. You're welcome back to this tutorial. In this particular video, I'm going to be explaining to us how we can load in our protein, our ligand, for different functions, okay, and perform different functions with it. Okay, I've already talked on introduction to some of options and tools here. Okay, so in case you haven't watched that, refer to the previous video and watch our introduction on PyMOL. Okay, so quickly I want to visualize my docked results. Okay, and we're using this particular PyMOL. I've performed molecular docking. I've generated different conformations of my ligand. I want to visualize the different conformations of the ligand in my protein using this particular software. Okay, to simply do that, I'll go to File to load in my protein and my ligand. I'll go to File, I'll go to Open. Okay, that's taking me to my file. Okay, what I'm working on is in my desktop. I saved it in my desktop, so I'll go to my desktop, and it's in my docking tutorial. Okay, this is my docking tutorial. Then I'll look for my protein. Okay, this is the clean protein. Okay, yeah, this is my clean protein. Okay, so I'll open it. This is it here. It has opened. Okay, can you see that it has opened? This is my protein. Okay, Can you see that? Okay, then I will have to load in my ligand too by simply going to open also. If you have followed our previous video, you will know that the output of the molecular docking is always saved in form of a ligand all. Okay, it's in a ligand all format. So I have to put this in all file. Okay, it's already in all file. So I will look for ligand all. Okay, look at ligand all here. So I'll click on it or double click on it, it will open. Okay, look at it, it has found its way inside my protein. Can you see that? Okay, let me zoom out to visible so that you see that. Okay, so look at it. See my ligand inside the protein. Okay, I've successfully loaded in my protein and my ligand into this particular what protein. Okay, as I told you, if I keep clicking on this, okay, these are the options. You see how my ligand will be moving inside the protein. Okay, this is the different conformations of the ligand generated at the cost of what molecular docking. So I have about 9 of them. Okay, if you also look at this column, you will see this is all okay for everything that is here. This is 2ACE, that is my protein here. That's the one that has this particular row. Any function I want to perform on the protein, I will do it with respect to this second row. Any function I want to do to the ligand, I will do that with respect to what this third row. Okay, any of this row you click on, can you see that? You click on, you on highlight will just leave the working space. Okay, so I will simply highlight it back. If I want the ligand to leave, I will just highlight it and it will be momentarily taken away. Okay, until return it. From the ligand, you can see 1/9 telling you that you have about 9 different conformations of this particular ligand inside your what your protein. Okay, so as you can see, I've successfully what loaded in my ligand and my protein into my what my PyMOL working space. Okay, in our next tutorial I will show you how you can continue or perform few functions with what you just loaded into the workspace here. See you in the next video. Okay, yeah, welcome back to the tutorials on PyMOL. Okay, and in this particular video, I'm going to be showing us how we can generate, a 3D view or a surface view of our protein. Okay, with our ligand after molecular docking. Okay, or you simply want to visualize a particular protein with a ligand in each surface view, okay, or in different formats you want to visualize it. Okay, but my main purpose of bringing my protein and my ligand here is simply to generate the surface view or the 3D view of this in particular interaction. Okay, so first of all, I love working on a white background, so I will change this to a white background by simply going to display, hit on display. Okay, then I'll go to my background and I'll change it to what? To white. Okay, so this is what I have. Okay, this is what I have. Okay, the next thing I need to do is to go to my action. Okay, I want to get in my active site, my polar region of this particular protein, because if I don't get the polar region, I won't know where the ligand is situated. So I need to get the polar region. Okay, so how do I do that? I'll simply go to my all. Okay, this action now is with respect to all I want to perform now. So I'll go to action in all by clicking on A. A means action, S means show, H means hide, L means label, and C means what? Color, as I've explained in our introductory video. Okay, I'll go to action, I'll go to precept. Okay, once I go to precept, I'll move by this stuff that come out. I'll go to what? To the ligand site. Okay, that's where the polar, the active site is. Okay, where the interaction of the ligand with your protein is taking place. Okay, I'll go to my ligand site and I'll change my ligand site to what? To cartoon. Okay, can you see what has happened? Can you see what has happened? Okay, it has exposed the active sites, interacting amino acids. That's what you can see like this. Okay, that's what you can see. So to see this more, I'll simply go to my protein and hide the cartoon of my protein using a H button. Okay, I'll just hide the cartoon, and once I hide it, look at what I have. Okay, so this is what the active site amino acid interacting with our protein. If I move, or if I change the different conformations of the ligand, you see how, can you see how the ligand is still just moving around inside this what active site, telling you that this is what, see, this is simply what the active site of this particular protein. Okay, so how do I do now? I've located the active site. I need to select these active site amino acid, okay, so that I can easily what, color them differently, or define them differently, and always refer to them anytime I want. So simply what do I do? I'll simply do what? Select by clicking on them. Make sure your cursor is on the line before you click. Your cursor is on the protein, on the different amino acids before you click. Okay, if you click outside, you will deselect everything, or if you don't want to deselect, you can hold down the shift button, okay, and be selecting. It's preferable you hold down the shift button and be selecting, so that in case you make mistake by clicking outside, you won't have to deselect or start everything afresh again. Okay, so I'm trying to select or highlight the different amino acids found in this particular word active site, okay, or what we call the polar interactions. Okay, this is what okay, I'm almost done selecting them. Okay, it's fine. Let me work with what I have already. In your own, you can select everything. Okay, so this is what I have. I've selected them. Remember, I didn't select the what, the ligand here. Okay, so I'll simply what, go to my selection. As I start selecting, another column will appear here, indicating the what, the selection I'm making. I'll simply go to the selection and go to action of that selection. I want to rename it so that it will bear a different name. Okay, I will now rename it. An option has come for me here to rename, so I'll simply delete this and write polar interactions. Okay, and I'll hit on enter, and it has shown what here. Okay, it has shown here. So I'm done selecting the polar interaction. Then I need to select the what, the ligand too. Once I click on the ligand, it shows me selection here. So I will also rename it by going to action and rename. Then it pops up here for me. I will save this as what, as ligand. Okay, and I'll hit on enter. Okay, and I've what, I've saved my ligand. I've saved my what, my polar interaction. Okay, I can simply now go to what, go to my all and continue my what, my actions or functions I want to perform with it. So in our next video, we'll continue on this particular step. We'll stop now. Thank you, and see you in the next video. Okay, you're welcome back to the tutorial on PyMOL. In our previous video, this is where we stopped. Okay, we've what, been able to select or define our polar interaction region. Okay, and also our what, our ligand. So what do I do now? I will have to bring back my entire protein and do my further, functions here, or perform further functions here. Okay, I'll simply do that by going to my protein now. This is the 2-ACE protein. Okay, I'll simply go to what, the show. Okay, and I will say show what, surface. Okay, you can show every other thing. If you want to return to cartoon, ribbon, and the rest, you can show here. But me, I want to generate, my task here is to generate the surface view, or the 3D view of my protein and ligand interaction here. Okay, so simply I'll go to my what, my surface. All these are what, different views you can generate. Okay, I'll simply click on surface. Okay, and once I click on surface, it has what, generated my surface. Okay, I'll simply go to zoom back or zoom to visible. Okay, this is it. Okay, but you may not see my ligand because of my selection. Okay, let me go to, I'll undo this. Okay, I'll undo this action. Okay, or rather, let me simply go to my what? My ligand, because my ligand has been put in surface view also, okay? Which, okay, my ligand is there, my ligand is there. I selected properly, okay? Can you see my ligand here? Can you, okay, don't worry, you won't see it properly like this. Okay, let me color it better so that you can quickly visualize that, okay? Look at my ligand. Okay, this is the entire protein. As you can see, by default, this software will color the different, chains of this particular protein with different color. That's what you're seeing, okay? But I can simply change this to a particular color. This is the protein. I'll go to the line and go to color, which is C, and I'll change it to, okay, I like magenta. Let me change it to magenta. Okay, this is what I have now. Okay, you can now see the ligand in there, okay? That's the ligand or the substrate of this particular protein. You can see how it's located inside the active site of this particular protein. Okay, how do I now define these polar regions? I'll simply go to my what? My polar interaction and go to color and change it to a different color. I'll change it to light blue, okay, so that it will be visible. Can you see that? Can you see that? Can you see that I've changed this particular polar interaction to what? To light what? Blue. And I can now see the difference from the rest of the protein here. Okay, the ligand now, I still need to change it to something else, okay? That green is not too visible. So let me change it to red. Since it's in a white background, I'll change it to what? To red. Okay, can you see that now? Can you see that now? See the ligand there, see the what? The polar interaction, and see the what? And see the rest of the what? The protein. So with this, I have been able to generate my surface view of my docked result, okay? Showing my ligand and my protein and the polar regions and the whole interaction, okay? This is how we can what? We can generate our 2D, our 3D or surface view of our protein interaction. If I keep hitting on this next button, okay, if I keep hitting on this next button, can you see how the different conformations of the protein, of the ligand in the protein is? Okay, can you see them? As I keep clicking, it will be reading until it gets to 9/9, telling you it has been completed. If I click back, it will start going back to 1. Can you see how the interaction is going? Can you see the different conformations? Okay, then sometimes, let me down show us, if you look closely to this, you will see something like a yellow, a yellow bonds you can see. Okay, can you see this? I'm pointing. These are the bonds, okay, the interaction. Usually the hydrogen bond interaction with our strong bonds, okay? So when you see this in an annotation, those particular amino acids that didn't pick or select, as you can see, these are them, okay? That's why they couldn't change in color, okay? But I'm showing us that this yellow color simply indicates what? The interaction that exists, okay? The different bondings in the active site, you can see them from here, okay? You can easily see that through that, okay? So this is what I have after generating what? My surface view of the protein and ligand interaction. Okay, in our next video, I'm going to be showing us how you can easily or quickly export your just visualized result or your work after you have finished what you want to do with it. See you in the next video. Thank you. Okay, you're welcome back from the tutorial. Okay, this is where we stopped in our previous video. We have been able to generate our what? Our 3D view or the surface view of our what? Our protein and ligand. Okay, so this is what we've been able to arrive at. Okay, in this video, I'm simply going to be what? Showing us. Okay, in this video, I'm simply going to be what? Showing us. Remember, as you click on any of this particular one makes it play very fast. Okay, you can pause it. If you want it to be seen one, you can just be clicking on the next. Okay, that's this option here. Feel free to play around that and enjoy the view. Okay, so here I want to save my words, my results. Okay, this is the result. I want to export it. Okay, I will simply go to my what? My file. Okay, remember, because this is what? This is the trial version. Okay, you can see something like this. okay, telling me that I have 30 days to license this. Okay, so this I'm working on now is on what the trial software I'm using. Okay, so later I will license that. In case you perform any work here, okay, and you want to see only this here, after generating your image, you can simply what, crop this out. Okay, but don't pay to license your app as soon as you install them, as soon as you are able to. Okay, but for the purpose of your learning, for the purpose of your practice, you can easily crop this out. Okay, once you have generated it as what, an image. But after everything, make sure you do what, you license your app. Okay, to export this or to save this, I'll simply go to my file. Okay, go to my what, I don't want to save session, I don't want to export molecule. This is already an image, so I want to export it as what, an image. I will export it as what, as PNG. I'll click on PNG. Okay, it will tell me save PNG. I say yes. Okay, I'll click on it. Then it will bring me to where it can save. This is under docking tutorial. Okay, if yours is not under docking tutorial, navigate to where it is and make sure you save it into the same folder. I will target this surface view. Okay, surface view, maybe surface view 1. Okay, assuming this is number 1. Okay, I'll tag that surface view number 1. Okay, it's already in PNG file, so it's fine. I'll simply do what, I'll simply save it. Okay, and it has what, exported my what, my result. Okay, I'll simply go to my file. I'll minimize this, go to my file. This is my file. I'll open it, the docking tutorial file where I saved it to. Okay, as you can see, it's supposed to have appeared here. Look at it here. Okay, if I double click on it, it's supposed to what, open up as the image I've just saved. Okay, is opening. Okay, it's loading, it's opening. Okay, it has opened. Okay, so this is the protein I've just prepared now. Okay, this is what we worked on, and this is the result. So you can easily crop this out if you haven't licensed your app and work harder to what, to license it. Thank you, and see you in our next tutorial.
Tutorial class today. In this particular video, I'm briefly going to be showing us how we perform site-specific molecular docking. All right, many people have been performing blind docking. All right, and it could be a bit stressful when you are trying to, locate a particular uh, binding site or active site where you have cases of more than one binding site in the protein, and you are trying to locate your binding site of interest. While performing blind docking, you could find your protein, all right, or your target or your ligand binding to different pockets of that particular protein or target, which is simply because it's a blind docking. But you could actually target a particular, pocket or a particular amino acid in the pocket of interest. Usually in every pocket, there are what we call, in every active site, there's what we call the committed amino acids, or the catalytic residues, or the active site residues of that particular active site. These are amino acids that are directly involved in the catalytic mechanism of that particular um, pocket or that particular active site of that protein or target. All right. For some of us that know about chymotrypsin, you discover there is three major amino acids in the active site we call the catalytic triads. These three amino acids are responsible for the substrate or ligand interaction, electron attraction and distribution, and all that, leading to product formation. However, in this short video, I'm going to be showing us how you can actually target a particular amino acid in the active site of your interest, causing your ligand or your synthesized product to only bind at that particular pocket. All right. And in this case, you don't just target the amino acid of interest, you actually target a particular functional group in that particular amino acid, all right, that will help you to strictly adhere to that particular pocket and that particular amino acid during your docking processes and all that. So, however, before you could do this, you should have undergone some, active site study, which we discussed in our introduction to CADD studies and all that. You're supposed to know about the active site residues of this particular protein, which you can find out through existing literatures. You're supposed to know the active site amino acid, which of the amino acids should be targeted, all right? And you should also have another tool, which I'm going to expose us to later on, that will help you expose the different, coordinate or centers or dimensions of the different amino acid in every protein or target you are working with. When you're able to get that, you can actually pinpoint a particular amino acid you are targeting and all that. So let's get into that quickly. I'm going to be working with cyclooxygenase 2 here because of its unique nature, all right? That will help us to grasp the information proper. So I'll simply go to my file to load the target. I must have downloaded it at this particular point. So I will go to my download where I have that. I've already saved that in site-specific docking folder. All right. So this is my target or my protein. So I'll simply double click on that to open. All right. So this is my target. Of course, we can see that. So I have a whole lot within here. So I need to clean up this, including the water of crystallization. All right, let me make this a white background for more a clearer view. So as you can see here, there are some dots, some red dots you can see. These are the water of crystallization. Yeah, for some of us that are into this already, you should know what that means. So what do? I'll click on this arrow to bring up what I actually have here. So I have two chains here, which is chain A and chain B. So I need to get rid of chain B so I can be able to see chain A properly for the study. So I will highlight on B and click my delete button. I'll highlight on the second B to delete the ligands of B, and then I'll highlight on the first B. As I click on this, you discover uh, the the subunit here getting highlighted and all that. So I'll click the delete button. All right, I only have chain A here. All right, however, I still have a whole lot of things in this chain. So I will first of all delete the water molecules, all right, which are the co-crystallized water molecule, water of crystallization, because this target is actually got through um, X-ray crystallography method of structural elucidation. All right, so I have my targets now and different ligands. All right, okay, let me highlight the target so that you can see the ligands. Yeah, these are the co-crystallized ligands. All right, these are the co-crystallized ligands. All right, so which I need to take care of. However, um, if I unhighlight the protein, I'll discover that there are actually ligands here, such as this, such as this, such as this. These are actually ligands binding. Look at this. These are not actually binding in any pocket. All right. This might just be molecules that were added in the process of structural elucidation for probably structural stabilization and all that. So at this point, I need to get rid of them, leaving only those binding within the pocket, such as this inside here and then this inside here as well. So what do? I will highlight the protein so I can see this visibly, and then I can now highlight this here to get rid of them by clicking the delete. Okay, I will highlight that proper. all right, and then I'll hit my delete button. Similar thing I will do here. I'll highlight this and hit on this to go, and then I'll highlight this and hit on delete. Okay, I'll highlight it better and hit on delete to go. Okay, so this is what I have. So I'll delete it. I have this as well. All right, I'll delete it, and then I have a group here which I don't need, so I'll delete as well. All right, so this is what we have. Okay, I still have a group here, so I need to delete that as well. So this is what I have here. All right, this is what I have. So as you can see, I have my ligand. I have two ligand here. Like I've mentioned earlier, this is the cyclooxygenase 2, all right, that has a membrane binding pocket, which is here, and then a heme binding pocket, which is the peroxidase binding pocket. All right, the arachidonic acid will first of all bind at this particular pocket. All right, after being converted or oxidized to prostaglandin G2, this same group will be, channeled into the heme pocket or the peroxidase pocket, where it's going to be reduced to reduced prostaglandin that actually initiates inflammation and all that. So what do? I want to target this committed step here. This is the committed point of this particular catalysis, not the peroxidase side. However, as you can see, the peroxidase, if I highlight the protein back, you discover what I'm trying to say. This is the pocket for the uh, the inhibitor or the drugs. This is where we call the membrane binding domain. The membrane binding domain is here, whereas this is the peroxidase binding domain. Okay, let me zoom it closer. So as you can see, this is the peroxidase binding domain, and then this is the membrane binding domain. So here is where the arachidonic acid binds and is converted to oxidized prostaglandin before it gets to this particular pocket, which is the peroxidase actin pocket that gets that reduced to the reduced prostaglandin. So what do? My interest is into target this particular uh, site, all right, this particular pocket here. But when you look closely, you notice that this membrane, this peroxidase binding site is actually wider because of the heme group when compared to this. So when you perform a blind docking, your grid setup or centers will automatically generate your box at this particular portion here. All right, simply because it's more predominant here, it's bigger here. All right, so the protein will assume, and is also at the center, so the protein will assume this to be the main pocket here. However, this is the membrane binding domain is actually what? The main pocket. All right, so site directed docking is what will enable you to actually target this particular portion and get it right, not this particular portion. Secondly, I mentioned earlier that before you go into this, you must have carried out what we call um, an active site study. So I have also investigated from literatures, all right, that at this particular portion, what you have here, this ligand you have here is the naproxen, is an anti-inflammatory standard drug that was co-crystallized, all right, with this particular cyclooxygenase 2, and this is a heme group which is always present in any peroxidase binding site, all right, or pocket. So this particular inhibitor, which is naproxen, I have found out from literature that is actually interacting with three major groups. All right, one of the predominant group there is arginine 120. All right, and arginine 120 is predominant here because it is the amino acid that directly binds to incoming ligands or inhibitor. All right, it predominantly binds to what? Incoming ligands or inhibitor. So if you're able to target arginine 120 in this particular pocket, you will certainly you will certainly inhibit the binding of every other ligand or substrate or inhibitor that might try to come in here. So it's actually a better or a good point for targeting in this particular pocket. Also, You also have some other serine and tyrosine groups here that are involved in electron abstraction, all right, leading to arachidonic acid oxidation to prostaglandin G2. All right. So, however, for the course of this, we are going to be targeting arginine 120, all right, in this particular pocket. And also, for those that might not have good knowledge of the active site study, if you find out about the active site amino acid, which are always present in every in silico related studies about a particular protein, you could simply locate that particular amino acid. That amino acid will give you an idea of the pocket, the active site pocket. And this is what I mean. If you come to the left, you discover you have the first A, which is your your protein chain or your target, and then the second A, all right, which stands for your ligands or your substrate. So in the first A, which is my protein, I'm going to expand this protein. Let me see the amino acids all present in this particular protein. All right. So when you come to an arrow, there's an arrow beside the box here under each of them. This is A, this is another A. So here I have an arrow there. All right. So when I click on this first arrow here, it will open up this particular A, which stands for the what? The protein or the target, exposing all the amino acids, okay, that made up this particular target. So what do? I will navigate to arginine 120. This started with arginine, with alanine 33. All right, so these are amino acids, of course. So I'll have to navigate to the arginine 120 and click on it, so I can actually know where it is in this particular protein. All right, if I find it in this heme pocket, then the heme pocket is my active site. However, if I find it in this naproxen pocket, then the naproxen pocket is my what? My active site of interest or the committed site. So what do? I'll scroll down to arginine 120. All right, so this is arginine 120. I'll simply click on it. And when I click on it, if you come towards your right, you see it highlighted in yellow. All right, let's do that again. This is arginine 120. If I click on that, you see that highlighted here in what? In yellow. So what do? I can now right click after this highlighting. I can right click inside here, and then I will change my display style of this particular highlighted amino acid to what? Say ball and stick. Ball and stick will help me to what? Expose that. So I will click on apply and I'll click OK. I can now click outside. So if I click outside now, you have seen this is the alanine, the arginine 120 I just click now. If I turn it properly, you discover that this is the arginine, all right, and then this is the ligand. So this is actually in the pocket of the naproxen, not on the heme group. So this pocket is actually the first pocket, the membrane binding pocket, where the drugs or where drugs are targeted, all right, for inhibiting this particular protein of interest. So now I have located the amino acid I want to target. The next thing is locating the functional group in the amino acid you want to target. Of course, you won't go and target carbon of this particular group. Carbon is in the neutral atom, all right? So you don't target carbon. Rather, you target your nitrogen groups, your oxygen group, and sulfur, as the case may be, all right? Yeah, in few cases. So this is what I have. Then the next thing to consider is the closeness of these groups with respect to, all right, the ligand or the co-crystallized ligand. If you eventually have, which in most cases is recommended that download your protein or your target in a complex form, which means when it's co-crystallized with something, that will give you an idea of the native interaction of that particular protein or target with respect to its ligands or inhibitors. All right. So what do I have here? This is the arginine 120, and then this is the ligand of interest. If you don't have any ligand as a co-crystallized ligand, simply target the functional group of the amino acid of interest projected into the pocket. As you can see, here is the pocket. So if I'm targeting here, I should be looking at these three nitrogen group. All right, these are the three nitrogen group, but the closest here, as I can see, is this first one. All right, this is nitrogen, this is nitrogen, and this is nitrogen. This oxygen is facing downward, so I'll prefer the ones that are projected towards the ligand or projected towards the pocket. So what do? I'll click on this first group here, this first nitrogen here. If I click on this first nitrogen, if you look down your screen here, if you look down here, as you can see my cursor, you are going to see an atom. Okay, this protein, this is the ID of this protein 3Q7D, which is inherent of every uploaded protein, the PDB ID. And then this is chain A, and then in chain A, I have arginine 120. All right. In arginine 120, I have NH2. All right. NH2 group. Yeah, actually, in every amino acid found in this particular pocket, you have for all these different atoms in the pocket, the amine, the nitrogen, the carbon, all of them, as you keep clicking on them, you discovered the number or the code given to it here will be changing, which means you can actually target every functional group of interest in this particular amino acid. So the next tool we are going to be using is going to open up this protein according to the different amino acid in it and according to the different functional groups in the amino acid. So we can actually target a particular amino acid and a particular functional group in that particular amino acid. So what do? I'll click on this particular first one, which I'm interested in this study because it's closer to my ligand here, or is more projected into the pocket. So what do? I've clicked on it. If I look down here, I discover that this is arginine 120 NH2. Note that I have arginine 120 NH2. So is the nitrogen group 2, all right, of this particular arginine 120 that I'm going to target at the course of this, not just arginine 120, but the nitrogen group of this particular arginine 120, the NH2. So I have noted that. So what do I need? I need the center XYZ of this particular functional group here present in this amino acid. All right, so I'll simply pick this particular numbering here, NH2, and use the next tool I'm going to show us now to do what? To actually get the coordinates and then certainly load the coordinates in my config file, of course, and then perform my docking study. And I will find my ligand strictly binding on this particular pocket, trying to locate or interacting with this particular target here. And the binding poles or the predominant poles that actually interact, or the pole that the positioning that actually interacts with this particular amino acid of interest forms your your best binding poles or binding model, all right, or binding mode as the case may be. So what do? We'll quickly load in our next tool that will help us locate the center XYZ of this particular nitrogen group of this amino acid. So I will quickly do that. We do that using Gauss view. All right, Gauss view is the tool. So I'm going to open Gauss view. All right. Okay, it's trying to load. Okay, so I'll simply click OK, and then I'll click OK. All right, it has loaded, so I can close this, minimize this, and then I'll maximize this. All right, this is the tool. It's Gauss view. All right, you can reach out to us in the um, comment section. If you don't have access to this tool, we can easily provide you with one. So I have to load in my protein of interest immediately. So however, before I load it in here, I will have to save my clean protein. All right, I'll have to save this protein as a clean protein so I can be able to visualize that in that tool, okay, as a normal clean protein. I don't need all this ligand. I've been able to succeed by investigating arginine 120 with respect to this ligand. So what do? I'm going to delete my ligands. All right, I'm going to delete them so I can have only my protein here. As you can see, this is only my protein. All right, so I'm going to save it first into that same folder I'm working with. I'll save this as my clean protein. All right, my clean. Okay, no, I need to save that. I'll go to my file, I'll go to my save as. All right, and then I'll save this as clean protein. All right, and I'll change the file type to pdb file. All right, so I can save this. So I can simply go to that tool right now. I'll go and load the clean one. Don't load the one with the ligands and all that. So I will go to my open, and then this is what comes out. So I will have to navigate to my folder. All right, is in my downloads. So, and is in site specific. So I will navigate to S. Okay, so PQRS. Okay, so I can get, this is site specific docking. So I will open it, and then this is my clean protein. Yes, I'll say all right, no problem. Okay, so this has loaded. As you can see, this is the protein. However, you will not be able to see it more clearly this way. So I will minimize this particular pop-up window, and then I will go upwards towards second to the last button here. As you can see, second to the last button here, if I click my mouse on it or hover my mouse on it, you will see view/edit file. All right, you see view/edit file, while the last one is stream output file. So no, you go to what, view and then /edit file. If I click on that file, this will pop up, so I can easily expand this. All right, so as you can see, this is the first group which we saw there, which is alanine 33. If you can remember, alanine 33 has how many atoms in it? About 5 atoms. All right, and you can see the different XYZ with respect to the different atoms of what the alanine 33 our target started with. However, I'm going to go down to arginine 120. This is the numbering I'm following here. All right, so I'm still at 70, 80, 90. So I'll go to 120. All right, this is 120. Can you see this? This is 120. All right, so I'm going to look for NH2 of 120. All right, if you remember in our target, all right, if you can remember in our target, this is it. Okay, we were interested in what? NH2. As you can see that down here, you can see NH2. So I'll simply go down to the same tool. This is my arginine 120. So I'll find the NH2, which is this, all right, of this group. So I will now move to the XYZ coordinate of it. All right, this is the XYZ coordinate of it. This is X, this is Y, and this is Z. All right, so before I do that, I will go and get a config file, all right, into this particular pocket, all right, that can help me edit that. All right, let me look for a particular config file. This is one. All right, so I can easily copy this. Before you perform a site-directed docking, of course, you should have your config file in there as well. If you don't know how to prepare this, you check our previous video at our channel. You'll find out how this has been prepared. All right. Okay, so this is the file I have. I'll open the file, and then this is what a config file looks like. Okay, it has your receptor, it has your ligand, and then you have your syntax, and then you have your sizes and all that. All right, my major interest here is in the syntax. I have syntax XYZ. Okay, this will inform the grid box you are going to be using with respect to this particular docking. All right, so what do I have here? I'm going back to that tool and copying the XYZ and simply replacing this portion with my XYZ value there. So I'll simply go back to the tool. All right, this is it here. No, this is it. Okay, so this is my XYZ. This is NH2. All right, so I'll copy the XYZ here. This is it. All right, and then I can simply copy, or you right click and then copy. Is that fine? So you can now go to the tool here, and sometimes what I do, I'll simply paste it. All right, so I can be copying it or cutting it one after the other. So I will do Control X and copy it and come here and replace it. All right, by doing Control V. Then I will copy the next one or cut the next one, and I'll come here and replace it with this. And then the next one is 22. I'll cut it, and then I'll come here and then I will replace it with this. All right, so this is what I have. So I have ended up replacing this. If you have gone through different videos or tutorials on molecular docking, you discover that this particular center XYZ will form a box where your ligand is going to dock in, or is going to bind in the pocket of your protein or your target. All right, so this have automatically commanded this ligand, all right, which is naproxen to this, assuming this is my what, my full config file. I've commanded this receptor to bind this particular ligand at this particular centers or this particular grid box, all right, using these sizes and giving me out my product as what, as a ligand R PDBQT. Most of this you get that from different videos on our channel, as has been said before. So this, with this, you have ended up getting what, your ligand to dock against your target of interest. So with this, you can continue with your command lines, trying to cause this docking to take place. So immediately you perform docking using this particular config file, your ligand is certainly going to bind at this pocket, and out of the conformations, most of them will certainly interact with arginine 120, which we have targeted in the course of this particular investigation. So this is what we call site-specific molecular docking study, or site-specific docking, which is far much more preferred than blind docking that most people do. So I will encourage you to practice this severally and make sure in all your docking you perform site-specific docking instead of normal blind docking that most people do, which is not actually the best. This will give you a better result and a more informed study. Thank you, and do not forget to always check up, or rather subscribe to our channel, Teach Yourself series. You'll find the channel link on our description. Okay, you can easily log in there, get subscribed, click on the notification button to be updated. Every week we update students with information like this. All right, the more they make inquiry from us, we make more videos and upload it over there, just to increase their learning process and all that, so they can as well perform more interesting studies with respect to, or in every CADD related researches. So don't forget to subscribe, click the notification button to always get informed whenever we upload a new video like this. It's free and you can always learn instead of paying heavily for some of this. Like I said, if you like any of our CAD tool, simply reach out to us through the comment section with your email address, and we will certainly forward that to you. Thank you, and see you in the next video. All right, you're welcome back to tutorial video. In our previous video, one of our videos, we mentioned or guided us on how you can carry out your post-docking analysis, uh, which is trying to find out the pose of your ligand within the pocket of your target or the active site of your target. And secondly, how you can find or discover or investigate the nature of the interaction between the ligand and the pocket or the active site of your target or protein. and of course the binding affinity. All these were covered in a previous video on post-docking analysis. In this particular video, I'm going to be guiding us on how you can find out or discover the best pools of your protein ligand interaction. Of course, after molecular docking studies, there are several poses or conformations of your ligand within the active site of your target of your protein. For instance, if you docked or perform molecular docking using Autodock Vina, at the end of the docking studies, about 9 different conformations of your ligand within the pocket or active site of your protein will be generated. All right, so out of this 9, you are only meant to pick just one best pose out of these. All right, so how do you determine the best, uh, protein ligand complex or interaction or pools, all right, to report in your study or to interpret as your result? All right, few steps or few guides uh, are what you're going to be considering, which I'm going to show us at the course of this particular video. They are quite simple to do. However, you need to be informed in order not to make mistakes or get things mixed up. All right, the first thing you do whenever you want to perform um, a computational study or molecular docking study, which is in silico study, trying to discover the drug candidacy of your compound or synthesized compound or synthesized product against a particular target, investigating a therapeutic effect or any form of protein ligand interaction study. So whenever you have such uh, in mind to do, it's necessary that at the end you should be able to find, a best pose, all right, for your particular study, which will inform you make a better choice or a better decision with respect to your study. All right, so the first thing, like I mentioned, you are supposed to do is to study. The first thing is to study the active site of your protein of interest or of your target. Yes, most drug candidacy are targeted at the active site of the protein, except when the drug candidate or when the target has an allosteric effect, which means when your protein has two pockets, all right, one as the active site and the other as the drug binding site or the allosteric site or regulator site, effector or inhibitor site. What it means is that you need to understudy your protein, know the pocket that is targeted in drug development or in therapeutic studies. Yes, this is important because certain proteins might have more than one pocket. An instance is the one I'll be showing us here, which is the COX-2 protein or COX-2 target, usually employed in the study of anti-inflammatory studies, all right, or anti-inflammatory effect of synthesized products or identified compounds. All right, when you're doing that, if you're careful enough, you'll discover that the same target has two binding pockets. All right, the other, which is the first rate limiting binding step or pocket of that particular target, where drugs are actually targeted, because that's the point that catalyzes the rate determining step, which is the conversion of the arachidonic acid to prostaglandin G or oxidized prostaglandin, which is the first step of the mechanism that leads to inflammation. Of course, uh, we won't go into the details here, but this particular protein has two pockets. The second pocket is the reduction pocket, where after the first reaction at the first pocket, it's moved to the second pocket. So most drug candidacy are targeted at the first pocket in order to inhibit even the second from commencing. So when you have such, the only way you could understand all this I'm saying is when you take time to understudy your protein of interest or your target of interest, have a good knowledge of the active site residues of the protein of interest, not just knowing the names or the different residues involved, but also the duty or functions of those residues within the